Okay, good morning, everybody. It's 8 o'clock, so it's time to start. On behalf of my colleagues, I'd like to welcome you. My name is Ned Mohan. I hope you are doing well in this pandemic period, and you and your family. So we have had a pretty robust enrollment. I think approximately half the US universities offering power are represented here. So it's kind of an humbling experience to have so many joining us here. And so humility is the operative word. And so the objective of this workshop is to disseminate our ONR funded curriculum. And Captain Peterson is here from ONR, and he will give his perspective. And this dissemination is taking place through an NSF sponsored workshop. And Dr. Aranya Chakravarti is here to tell us about the educational and research opportunities at NSF. And one very important objective of this workshop is to get your feedback as we go forward. What can we do to improve whatever we have done? So we have developed many labs and many undergraduate and graduate courses. And many of the developers are here in the 10:30 session. And not all, but many, and those who are not here, I will catch them during the next workshop. And so why have we developed this? Basically to enable other faculty and other schools to take whatever material they choose to teach their own courses to their own students. So this material is basically aimed at faculty, but of course it can be used by students as well. And we are uploading all this material to our web portal CUSP, and it's downloadable from there, totally free of charge by anybody. One doesn't have to be a member of this CUSP, although 235 US universities have seen fit to become members. Okay, and these are foundational courses. These are courses that power engineers. Power, we use it in a holistic sense, but they need to know. So this is a workshop after all, so please ask questions through this Q&A option that you have on your screen. And so, that's the way we will get your feedback and have a discussion, which is very important objective of this workshop. And two of our PhD students, Dan Kelly and Jairam, they are also monitoring what's going on. And if I stumble, I'll ask their help. I'll request their help. So with that very brief introduction of what this workshop is all about, I would like to invite our department head, Professor Randy Victoria, and I'll read a very short bio in order to kick off this workshop by presenting a few welcoming remarks. So I'll read his very short bio that Professor Randall Victoria received BS degrees from MIT in 1980, a PhD from UC Berkeley in 1985. Then he joined Kodak Research Lab, where he worked until joining the University of Minnesota in 1998. His research interest is theory and simulation of magnetic materials, primarily directed towards spintronic memories, microwave interactions with magnetic materials, and magnetic recording hard disk drives. He is best known for his work on recording media, for which he has received several awards, including the Achievement Award of the IEEE Magnetic Society. He has served as president of the IEEE Magnetic Society and as general chair of the 50th Conference on Magnetism and Magnetic Materials. Professor Victoria is a fellow of the American Physical Society and of the Institute of Electrical and Electronics Engineers, IEEE. So with that brief introduction, Randy, it's the stage is yours. Thank you for being here.
Thank you, Ned. So I'm going to spend just a minute or two introducing you to the University of Minnesota, our department, and Ned himself. So University of Minnesota is located in the Twin Cities of Minneapolis and St. Paul. It's a very large campus with about 50,000 students. At one time that was second largest in the country, although I don't think that's true anymore. The department, however, is not correspondingly large. We have 45 tenure track and tenured faculty, plus 6 research and teaching professors. We are, however, very old. We were founded in 1886, which according to at least one list, makes us the second oldest department in the country, tied with MIT, though I think there are a couple of lists here that don't always agree. I'd like to spend just a minute talking about Ned. Ned has a very distinguished history in power electronics, as probably most of you know. He has won many awards, and he's written 6 books that have been translated into 9 different languages. His books are used in more than 150 US universities, plus many, many international universities, but we don't have a count. He is a member of the National Academy of Engineering, and most recently he won the, he was selected to be a Regents Professor of the University of Minnesota, which is the highest honor that the university gives to their faculty. So with this, I turn you back to the more interesting part of today and back to Ned.
Okay, thank you very much, Randy, for those kind remarks. I really appreciate it. Whatever I have done has been with the support of my colleagues, my department heads over the years, and also the staff. But first and foremost, I've been very lucky to have very nice, very top-notch graduate students. So with that, I would like to invite Dr. Aranya Chakravarti at NSF to give his perspective why NSF has supported this workshop and what the educational and research opportunities are in his division. So Aranya, thank you very much for being here. And I will read your short bio. So he has a very distinguished career already. And as you can see, he is quite young. So these are quite, but I have tried to shorten it as much as I can. So Dr. Chakravarti joined NSF as a program director in August of 2020. He is a professor in the Electrical and Computer Engineering Department of North Carolina State University of Raleigh, where he is also affiliated with the NSF Freedom Center. His research and interests are in areas of power systems, control systems, optimization, and machine learning, with applications to both transmission scale and distribution scale power grids. He has published 3 books. Since joining NC State, he has graduated 10 PhD students and has supervised 4 doctoral researchers. From 2016 to 2020, he served as an associate editor for IEEE Transactions and Control System Technology, and currently serves as an editor for IEEE Transactions and Power Systems. Dr. Chakraborty received the NSF Career Award in 2011. His research group at NC State has received the Best Internet Application in Energy Award for US Ignite in 2013 and 2014. In 2019, he was named a University Faculty Scholar by the NC State Provost's Office. So Aranya, with this very short bio of yours, the stage is yours, so please.
Thank you. Thank you, Ned.
Sure.
I didn't realize that I will be like so upfront in the agenda. I thought that my turn will come about like half an hour after or something, but thank you. So Dan, how do I screen share my presentation? It says the host has disabled participant screen sharing.
You should be able to now.
Okay. Okay, I'm hoping that everyone can see my screen. Ned, can you see my screen?
Yes, we can.
Okay. Well, thank you, Ned, for the introduction. And good morning, everyone. I'm very pleased to be here in the workshop, and I'm also very glad that I'm technically the first speaker. So as Ned mentioned, I'll be brief. So this is basically an update on the power and energy program that we are doing here, the work that we are doing here at the US National Science Foundation. My name is Aranya Chakraborty. I'm a program director in electrical communications and cyber systems. We also abbreviate that as ECCS division in NSF. And I am making this presentation on behalf of my entire team, which actually consists of 3 people, namely myself and 2 of my other colleagues, Dr. Kishan Baheti and Dr. Donald Wunsch, who are the other 2 program directors in our power and controls team here at NSF. Before I actually go into the specifics of the actual work that we are doing in the power group, I just wanted to mention a couple of administrative slides to give you guys an idea about how NSF works and how the different administrative structures in NSF work. So this may be a redundant slide because most of you actually know about NSF, but just to give a definition of what NSF is and who we are. NSF is an independent federal agency created by the US Congress in 1950. With the intent of promoting the progress of science, including engineering science, and with the goals of advancing national health, prosperity, welfare, and national security. And we are also the only federal agency whose mission includes the support of all fields of fundamental science and engineering, including power system engineering, which is, of course, the main focus of this workshop. And that's primarily the main reason why NSF has been funding NED's workshop for many, many years now, because power engineering is at the forefront of our mission. Just to give a little bit of a structural information about how the workflow in NSF works. So we have our, within the Directorate of Engineering, we have our Assistant Director, Dawn Tilbury from University of Michigan. We use a lot of abbreviations here at NSF. We refer to her as our AD. And then we have our Deputy Assistant Director or DAD, Dr. Linda Blevins. And then under the Office of the Director, we have 5 different divisions or departments. The structure in NSF actually is quite similar to the way administrative structures work in the university. So you can imagine that the AD is sort of the dean. And then under the dean's office, we have 5 different departments. Here we call them as divisions. The division there where I belong to is ECCS, as I mentioned. And our division director, which is equivalent to sort of like a department head, is Dr. Shekhar Bansali, who is also relatively new, just like myself. He has been here in NSF for about 6 months now, and he joined as our DD starting last August, I guess. And then some of the other divisions we have are civil, mechanical, manufacturing, and innovation, which is CMMI. We also have chemical, bioengineering, environmental and transport systems, which is CBET. Then we have the engineering and education centers, which is EEC. And then we have the industrial partnerships, which is IIP, which is abbreviated as IIP. So let me tell you guys a little bit about the specifics of our division, which is ECCS. This is the division which deals with every aspect of electrical and computer engineering. And within the division itself, we have 3 different groups or clusters. We have one cluster which is referred to as CCSS, and that cluster deals with communications and circuits and sensing. We have the second cluster, which is abbreviated as EPMD, and that cluster deals with research in electronics and magnetics and photonics and material sciences centric devices. And then finally, the cluster where I belong to is called EPCN, which stands for Energy, Power, Controls, and Networks. And this is the cluster where we do all the power system and control system related research. So just wanted to give you this is a busy slide. You don't have to go through all the names, and I'm also not going to say each and every name over here, but just wanted to show you guys a glimpse of our division or our department, and just to show you who the different people involved in the division are. So if you look at the EPCN program, you will see that currently there are 3 program directors, including myself, Kishan and Donald. We used to have Tony Koo as our third program director, but Tony finished his term as a rotator and went back to University of Hawaii. And then Donald actually just joined from the beginning of this month. So he's probably like a week old or something at NSF. So he's our new program director. And then aside from the program directors, we also have an expert in power electronics, Dr. Ali Reza Khalid. He's from University of Maryland and he handles the power electronics program within our cluster. And then we have several AAAS fellows who help us with some of the administrative duties and education and outreach programs. So as the name suggests, right, so EPCN mostly handles three different types of pillars. The first pillar is control systems. The second pillar is power systems and power electronics. And the third pillar is machine learning and data science. So let me just quickly give you an overview of the specific topics of interest within control system thrust. So of course, we handle a lot of proposals on core control theory, including robust, optimal, nonlinear, and adaptive control. Lately, we have also been paying a lot of attention, and our focus has been quite a bit on data-driven aspects of control, applications of reinforcement learning and deep learning in the context of control. We are taking part in a lot of new conferences such as L4DC and some of the workshops that are going on, including new RIPS and ICML, for example. We are taking a lot of interest in some of those conferences which are at the intersection of machine learning and control theory. Also, the controls program is mostly handled by me and Kishan, and we also handle a lot of programs and proposals at the intersection of multi-agent control and network dynamic systems, and reliability, safety, formal methods, information theory, cybersecurity, and resilience. Then within the power system thrust, and that is really the main program which I handle and which is probably of most interest to this audience. Within the power system program, we of course deal with traditional topics in power, including transmission systems, distribution systems, and generation. Lately, there has been a lot of focus on the topic of climate science, on the topic of climate change in particular. And some of the topics which are related to climate change, I'm highlighting here in red over here, that use of distributed generation and microgrids, impact of high renewable penetration, including wind, solar, and other inverter-based resources, consumer expectations and demand response, need for resilient grid operation in the face of natural disasters. There have been, if you look at the career awards that were made this year, I funded, I think, around 3 career proposals, which are around the topic of resilient operation of power grids in the face of different kinds of natural calamities, including wildfires and other natural hazards. We also deal a lot of power system proposals at the intersection of cyber physical systems, including cybersecurity of power grids. How do you use massive amounts of data at both transmission scale as well as in distribution scale for making real-time decisions in power system controls? And of course, as I said, Ali Reza actually deals with a lot of power electronics proposals and proposals on electric machines, which is also probably of much interest to this workshop. And how do the integration of modern power electronics impact power system operations, power system stability, and in general, the functioning of power systems in both generation, transmission, and distribution scale. So we are also interested in quite a bit of in learning about those new areas at the intersection of power electronics and power systems. Within the machine learning and data science thrust, this is not my core area. So Donald Wunsch is the one who handles the core machine learning program. And some of I'm just going to read verbatim some of the main topics which Don handles, including neural networks, deep learning, neuromorphic engineering, data analytics and intelligent control, machine learning hardware. Tony actually, before he left, Tony did a NSF workshop on the hardware aspects of machine learning, which was very, very successful. And I think all the details have been, made public, and, you can access all the information about the workshop if you're interested. So just, you can email me and I'll point you to the workshop website. Machine learning algorithms, analysis and applications, and also learning at the intersection of human-machine interaction. So let me tell you a little bit about the NSF 10 big ideas. So these 10 big ideas have been there for quite some time now. I think there are several of these ideas, including the quantum leap and the, the navigating the new Arctic and all that. But I think two of the most relevant topics that may be of interest to this audience is, first of all, HDR, which is harnessing the data revolution, and also the human technology frontier, work at the future of work, essentially. So, which of course is very relevant suddenly because of the COVID-19 situation. So we also deal a lot of, our division deals with a lot of proposal at the, about the future of work and how work is going to define the next generations of our society. Now, besides the research ideas, we also have some infrastructural ideas that we are trying to bring into the 10 big idea perspective. And I'm going to show one slide just in a little bit about what we mean by research infrastructure, because I personally am involved in one of the solicitations on mid-scale research infrastructure. And we also made a power system related award, which these are big grants essentially. And I'm going to tell you about the power system award that we have made just a month or month and a half ago to UC San Diego on setting up a campus-wide infrastructure on microgrids. So I'm going to mention that in just a minute. Now, besides our core programs, we also participate in several of the other foundation-wide programs. One of our main investments is in the area of cyber physical systems, or CPS, and CPS has been going on for a long time. It's like almost more than a decade, actually. And CISE, the Computer and Information Systems division, actually is the leader in CPS. David Corman is our cluster lead for CPS, but ECCS in general participates quite actively in the CPS program, especially from EPCN, because we get a lot of cyber physical system related proposals in power systems and controls. So if you just do a quick NSF search, you will see that hundreds of awards have been made in the power area over the last 10 or 11 years within the CPS domain. Another fairly recent, not very recent, but fairly recent investment of ECCS or even EPCN is in the area of smart and connected communities. There are, this solicitation has resulted in several power system related proposals, especially in the context of power system people working with power system researchers, working with people from economics, social sciences, behavioral sciences, computer scientists, and other policymakers to reach out to smart communities that will be benefited from fundamental research in the area of power and energy. Another new solicitation, this is a very new solicitation. I think it's probably in its second year now, which I personally am also in the working group of this one. This is referred to as the Sustainable Regional Systems, or SRS. And the solicitation actually became public about, I don't know, like a month or two ago. And here the idea is basically to connect concepts of rural systems. Like, for example, rural areas depend on urban areas for technology, while urban areas depend on rural areas for the basic needs of life, such as food and other, like farming, agriculture, irrigation, and all those other aspects of daily living. So this solicitation is basically trying to capture the interaction of this feedback mechanism between big cities and small villages, and how people and administrative structures in these two silos can work together with each other to make a better social interaction between rural systems and and urban systems. So also this has some overlap with smart and connected communities. There are people in the working group who work on both, including myself. So I'm also involved in smart and connected communities. So so we are trying to bring concepts together by which people from policies and economics and social and behavioral sciences can work together with power engineers and computer scientists for making this good bridge between engineering and social sciences. Quick slide on this new solicitation we have from within our division. So this is just a division-wide effort. It's not a foundation-wide effort. This is referred to as ASCENT, or ASCENT stands for Addressing System Challenges Through Engineering Teams. And the intent over here is that even within an electrical engineering department, we have so many different topics, right? Like signal processing, we have controls, we have power, we have wireless communications, we have networking, we have magnetics and electronics. So all of these sub-disciplines of electrical engineering, we often don't talk to each other, despite the fact that maybe like big overlaps between our research interest. And if we come together, we can solve some very challenging problems in engineering. So ASCENT was introduced from last year to bring these sub-teams of electrical engineering, to work with each other. And that's where the different clusters, EPMD, EPCN, and CCSS, we are working with each other to develop proposals that fall at the intersection of these different subdisciplines of electrical engineering in particular. And last but not the least, so this is probably my last slides. I wanted to mention about this mid-scale research infrastructure 1 and 2 solicitation. I personally am involved. I'm the engineering representative of mid-scale research infrastructure 1. So again, these are infrastructural investments. They are much more expensive awards. They are not technically research grants. So these awards are not meant to support graduate students. And the intent over here is not just to hire PhD students and postdocs and publish papers and go to conferences. The intent here is to build something an actual physical or hardware infrastructure, or even a software infrastructure by programming and coding. The mid-scale is again divided into 2 parts, 1 and 2. So the mid-scale 1 supports research proposals between $6 million and $20 million. And then mid-scale 2 is between $20 million and $100 million. So these are expensive infrastructural projects, but I still wanted to mention this because we recently, and by recently, I literally mean like a month ago or something, which became public, we made a mid-scale 2 investment to UC San Diego. We gave almost a $40 million grant to San Diego to create a nationally visible test bed for better understanding how to integrate distributed energy resources such as solar, wind, and smart buildings and electric vehicles into the power grid. And the goal is to make this test bed available to outside research teams and industry by 2025. So this is going to be, I guess, a game changer in the power and energy area, because, there will be a centralized test bed in the UC San Diego campus where other people can go and carry out their experiments related to integration of renewables and DERs and power electronics, smart buildings and electric vehicles and see the impact of this integration on the transmission scale grid across the entire nation. So I guess that's pretty much, sort of like a quick rundown of the different programs related to power and energy that we are working here at NSF. I did not cover quite the educational aspect. There's a huge, initiatives about education also going on in parallel to research over here in power and energy. Like, for example, we are doing this particular workshop with NED, which focuses primarily on education. We are also working on several other workshops which are going to happen in near future. For example, there is one coming up with Texas A&M with PCERC, where we are going to talk about research in power systems for grid at the edge. And there are also several educational initiatives, sub-initiatives involved with that workshop. So I encourage all of you to take a look at that and see if you can participate in the PCERC workshop. And aside from that, we actively take part in engineering education centers and research centers through the ERC program. And there also we are promoting a lot of workforce development as well as educational activities in the power and energy area including a recent one, which was a recent ERC, which was awarded to University of Utah, or Utah State, I guess. It's called the Aspire Research Center, which has to do with power electronics. Regan Zane is the PI, and our ERC program is funding his center, which is related to power electronics and the application of vehicular power electronics for better vehicle to grid integration. So these are just, just a quick information sharing. If you are interested in the specifics and the details, please let me know. You can just send me an email and I can point you to the right websites or pointers, or, most of these are public information anyway. So if you're interested, you can just do a Google search and that will take you to the right websites where you can get all the relevant information. So with that, I think that's where I will end my presentation, Ned. And if there are any other questions, I'm showing my email address over here. So please feel free to reach out. And I'll be very happy to answer any questions that you may have about NSF and the work that we do here at NSF. So thank you.
Yeah, thank you very much, Aranya, for telling us about the research opportunities at NSF. And I'm sure you'll be receiving some emails about what the opportunity.
Yeah, sorry. Sorry if I sounded a little groggy. I'm not a very morning person, so.
No. You are just fine. You are just fine. And personally, I have been very fortunate to have this workshop funded by NSF. And over the years, starting in 1991, I have organized over 35 NSF-sponsored workshops. Yeah. So I can't be thankful enough, I guess. So thank you again, Arina. So the main focus of our workshop is to disseminate all the curricular material and labs that we have developed through ONR funding. And it has been made possible by the vision of Captain Peterson at ONR. So Captain Peterson, I hope you are here. I don't see you on the screen, but I hope you are here and we will advance your slides on your direction. So let me just read a very short bio of Captain Peterson. He was with the US Navy, and after retiring from US Navy, he became a program officer of ONR, Office of Naval Research. He graduated from the US Naval Academy, Annapolis, Maryland, with a BS in mathematics in 1986, and was commissioned an ensign in the United States Navy, and he was selected for lateral transfer to the Engineering Duty Officer Program. He received an MSME from the Naval Postgraduate School, Monterey, California, in 1994. Following active duty, he was employed by the Naval Surface Warfare Center, Carter Rock Division, Annapolis, Maryland, as an electrical engineer. In May 2006, he was hired by the Office of Naval Research, ONR, serving as the ONR S&T rep to the Electric Ships Office, PMS 320. In November 2008, he was recalled to active duty with assignment as the Deputy Director, Electric Ships Office, PMS 320, assigned from 2008 to 2012. He was promoted to the rank of captain in 2009, later retiring from the military in 2016, following 30 years of service in the US Navy. So thank you, Captain Peterson, for your service. From 2012 to 2014, he was the Navy's Director for Systems Engineering in the Deputy Assistant Secretary of the Navy, Office of Research, Development, Test, and Evaluation. Following his service at DASN, RTD&E, Mr. Peterson returned to ONR and served as a program officer leading basic research in power electronics, electromagnetism, and adaptive controls and applied research in machinery, controls, silicon carbide, wide bandgap semiconductor applications, and medium voltage direct current power distribution systems. Married to Elena, they have 2 adult children. He's a senior member of IEEE, member of ASNE, and the MRS. He and his wife are active in their church and singing. So once again, Captain Peterson, thank you for your vision, for supporting us over all these years, and we really, really appreciate all you have done for us. So with that brief introduction, Captain Peterson, the stage is yours.
Good morning, Dr. Mohan. Good morning, everybody attending the workshop today. Thank you again for inviting me. Please drive on your end. That's fine. I cannot take credit for all the curriculum that has been developed and resulting from ONR funding. I would have to give a lot of that credit to Dr. Terry Erickson, who was my mentor, still is my mentor, and helps me with the wide bandgap programs. But he started a lot of this at ONR with the curriculum development, and I'm continuing that as a new technology, as new materials emerge. Some of the slides that you're going to be seeing in the presentation today, if you've attended these workshops before, look familiar. However, there are new slides because there's a new direction that we're going called PPEDS, Power Electronic Power Distribution System. And I'll be talking about that later in the presentation, but basically that incorporates a network of PEB-based converters. Now, if you're not familiar with PEB, many of us played with Legos when we were younger, Lego building blocks, and that's exactly what PEB is, but it's a power electronic building block, fully functioning and fully operational, that's programmable. And we have done a lot of work with initial PEBs, PEB 1000, PEB 6000, which is a 6 kV to 1 kV DC to DC converter. And then now we're building a Navy IPEB, which I'll get into later. And then all of this is supported by or housed by what we call NIPEC, Navy Integrated Power and Energy Corridor. And so again, I'll be getting into that later. So let's go ahead and get started reinventing power programs through sustainability focused curriculum. And I just plan to give an update on that today. Thank you. Next slide. So here's a brief overview. So for some of you who are not familiar with ONR, I'll be giving a brief mission, how we got started and why ONR is in business, motivation for power and energy, specifically the electric warship. Zumwalt is our first electric warship, although our aircraft carriers, the Ford class, have a 13.8 kV system, a grid on there where AC generators, but and also AC distribution. Macon Island, for example, LHD-8 is our first hybrid electric drive ship that uses a motor in conjunction with the gas turbine and has a clutching system where you can clutch out or clutch in the motor. And the ship saved about 500,000 gallons of fuel on its first voyage, and they continue to save fuel as they go forward with that platform. And then some of the powered energy technologies, beginning into component level development, specifically silicon carbide, and some of the technological advances resulting from ONR and other service investment. I'll be talking about Navy IPEB as well at the component level, but then we get into the system level and we'll talk about PPEDS, NIPEC, which I mentioned, as well as cybersecurity. All of these systems have to be able to function, and this may be an educational area too. Dr. Mohan is developing courses for cybersecurity with respect to power electronics systems, and I have a grant with Dr. Osama Mohammed at Florida International University that's finishing up in a new grant that's starting focused on the cyber physical systems for power and energy systems. Then we'll get into reinventing power progress through sustainability focused curriculum, and some of that curriculum and some of the current grants that Dr. Mohan is being funded under. We'll wrap things up with a summary and then how to get in touch with us. As a lot of these areas, if you have ideas, we're taking white papers, which eventually will lead to proposals in power and energy. I will say I have no further FY21 funding. All my FY21 funding has been exhausted. So we're going to be looking at this point at FY22 or FY23. Next slide, please. So ONR was founded in 1946, signed into law by our president, Harry Truman. Thomas Edison was involved with that. Navy Research Lab was involved with that. And our function through the years is to give advanced technology to our warfighters. Going back to what Teddy Roosevelt said, speak softly and carry a big stick. The United States is not an aggressive nation, but we do believe in strategic deterrence. And we do believe in carrying a big stick, and that is the big stick of technology. And going forward in the future, with where our missions are going to be relying upon is high voltage, high power, power and energy systems. And not our current Chief of Naval Research, but our former Chief of Naval Research, Rear Admiral Hahn, came up with this document. It's called Naval Research and Development Framework. And it has three functions and three A's there. One is to align. Many people are working on R&D, research and development, science and technology. And so we want to make sure that these priorities are shared, that they're not funded duplicatively, but that they are collaborative with each other. We also want, once we develop those technologies, we want to be able to accelerate that and get the technology-enabled capabilities in the hands of our warfighter. And then lastly, we want to allocate the resources, the funding that we get from Congress to speed these results to the warfighter in order to win. And what I mean by win is strategically win, so that there's no more wars, theoretically, no more battles. We need to be first to field decisive capabilities to our warfighters, so that other countries, rogue countries, for example, will not want to get into a battle or war with the United States. Next slide, please. And so this all begins with research. The framework has those framework priorities there, those 5 that are listed there. A lot of what we do in power and energy is under operational endurance, that third one down, but also scalable lethality. The first one comes into play. The CNR, Chief of Naval Research, has about a $2 billion portfolio that's spread across 6.1 or basic research, 6.2 applied research, and 6.3 advanced technology development. And it's a team. It's not just government, but it's a team consisting of government, academia, and industry working together in developing these technologies. Now with 6.1, most of that is academia because it's first principles. It's science, it's math, it's STEM, everything about STEM, it's materials. And as we go forward and as we mature that technology in 6.1 from a TRL 0 or 1 to a TRL 2 or 3, then we get into applied research. And if you look at the pie chart, that changes a little bit, where industry gets a little bit more in 6.2. Although academia still gets a good chunk in 6.2 and then government. And then lastly, as we had matured past applied research into advanced technology development, such as our innovative Navy prototypes, our future naval capabilities, industry gets a much larger piece of the pie. And that's okay, because we have our defense industrial base, and that's who does need to get the funding in order to get it across the valley of death into the Electric Ships Office, PMS 320's hands to go forward. So takeaway here is we want to accelerate knowledge to technology to capability. It starts with knowledge, then technology, and then into the hands of our warfighter and giving them capability. Next slide, please. So the motivation for a lot of this shown here graphically are some pictures. We want to optimize power density. Power density is important. With a terrestrial microgrid, you have a lot of space, and power density is not important. But on a ship where you have a limited space and limited volume, power density becomes very important. And if you could look at the ships that I served on 30 years ago, we had a total of 6 megawatts of installed power, but because of the ratings of the circuit breakers, we could only put 4.5 megawatts be made available. Today, if you look at the Zumwalt class destroyer, DDG 1000, that has 78 megawatts of installed power. And it's an integrated power system. The steamships that I served on were also an integrated power system because the generators were separate from the prime movers, which drove the ship through the water. The gas turbine ships, however, are not in of themselves integrated. Sort of where we're going with, in addition to that, is the reliance on semiconductors. I've got a 6.2 applied research program with silicon carbide, and we're making a lot of progress there. Several years ago, with combined DOE funding, we developed the XHV6 module that Wolfspeed has. It's a 10 kV, 240 amp module. And that again was developed by ONR with the Department of Energy. But in the future, we're going to next generation semiconductors, wide band gaps such as GaN, and even ultra wide band gap and extreme band gap semiconductors such as gallium oxide, aluminum gallium nitride, diamond. Why is that? Because the on-state resistance, number one, the on-state resistance of GaN is 3 to 5 times less than that of silicon carbide. So it's even more efficient. And secondly, silicon carbide has a limitation for continuous power MOSFETs. We like to use for that technology for continuous duty power. And it has a limitation of about 12 kV. And as my friend Anant Agarwal says, it sort of runs out of steam. But gallium nitride, I've got a program in 6.1 to get us to 20 kV in hopefully 5 to 7 years. And I've got some new efforts this year with Super Junction, with Penn State, NRL, and Virginia Tech developing Super Junction, sort of a hybrid lateral vertical device to get us to 10 kV. And then I have other programs with Stanford, with Virginia Tech, with University of Illinois, in collaboration with Dr. Kizayali at RPE Ishik, and to develop 20 kV devices for a 12 kV DC power distribution system. Next slide, please. Electric warship vision, I already mentioned some of this, but this is sort of gives you the motivation as to why we're going electric and high power. This also gives you the motivation in part as to why we need to train people. We can develop all the technologies that we want, but without people, engineers and scientists knowledgeable of these systems that not only have to design them, but also have to operate and maintain them, that also gives them the motivation for developing the curriculum that Dr. Mohan has and his team. But integrated power system, as I'm Zumwalt, in the future, we're going to integrated power and energy system for large surface combatant. We're getting ready to field a high energy laser this year on our LPD, our San Antonio class LPDs. EM gun is still land-based. There's still a vision to put an electromagnetic gun on a ship. And then also high-powered radar and electric auxiliaries. All of these are giving need for technologies that support these applications, but also the education and training that's needed behind it. Next slide, please. Power and energy is shown here. Again, I just spoke to some of these. Some of the technologies that we have developed under the PEB program, for example, have spun off into GE's wind turbine industry. We're looking at unmanned platforms, amphibious platforms, and the future surface combatant that I mentioned that's going to be high power systems. So a lot of our power and energy S&T is focused on first principles, as I showed earlier, but it also has application based shown here and contained by these slides. Next slide, please. And then shown here, I talked a little bit about this earlier. If you go to that lower left-hand corner where power and today sort of meet, that's where I was on our ships, 35 years ago. But then you can see where we're going in the future. And we've done sort of an incremental flight upgrade. But as the capability demand, you can see in the red line, it's just not keeping up with it. And this also applies to education of people, of our students, of industry, of our government workforce. And then I mentioned earlier about the energy going from IPS to IPES. The reason for that is very similar to a microgrid where you have stochastic sources like the sun, the tidal, the wind. On a ship, the loads tend to be stochastic. And they don't provide a nice clean waveform that a 60 hertz generator would like to see. So you really need energy storage, and you need training in energy storage to be able to facilitate those needs and those as shown there in that mission power demand stochastic profile. Increased warfighting capability to overmatch the threat demands power, not only power, but also energy. Next slide, please. So now we're going to get into some component level development. Next slide. And I mentioned Terry Erickson's name earlier. Not only was Terry Erickson instrumental in seeing the need for education, he was also instrumental in starting the PEB program at ONR back in 1994 when he came from David Taylor Research Center, Naval Surface Warfare Center at Annapolis to ONR. And you can follow that path over time as to where we've come with the power electronic building block to developing that 10 kV MOSFET there in 2016 with DOE and ONR funding, to where we're going, where we're at today with this Navy IPEB, which I'll talk about later, and then getting into this PPED system. Hopefully by 2026, we'll have a working PPED system that incorporates source converters and load converters for the PPED system that's housed in a Navy integrated power and energy corridor. Again, the concept of the silicon carbide PEB program, it's a building block. It's a least replaceable unit. We're hoping one day to be able to, like you do on your computer, to remove a USB, right mouse click, then safe to eject, be able to eject these PEBs should they fail. But we're trying to develop them with increased reliability, hopefully to get about 200,000 hours in between failures so that we can schedule maintenance around this. And so as silicon carbide plateaus in 10, 15 years and in other technologies such as GaN or other ultra wide bandgap technologies take over, we can replace these PEBs with the new ultra wide bandgap technology. Next slide, please. Some of the technical advances that have allowed us to get here are silicon carbide power switches switching at greater than 100 kilohertz, switching free. Navy IPEB, for example, is switching at 500 kilohertz switching frequency at 1/4 of a megawatt of power, and has about 12 kilowatts per liter volumetric power density. A lot of work has gone on over the years with field programmable gate arrays, high speed control. The next step is to be able to develop intelligent power modules, be able to have these PEBs that can be downloadable, very similar to like your iPad or your iPhone that operates under an iOS system, be able to have downloadable knowledge and programming into these PEBs so that they can function and do the mission or the concept of operation that the ship needs it to do. High frequency magnetics is not a solid green, that's a gap area. As we get past 500 kilohertz and 500 kilowatts of power, we find limitations. The nanocrystallines and the ferrites and things of that nature start to not be able to keep up. And so I've got an effort started this year with Raju, who left General Electric and is now started his own company, FastWatt, along with the University of Pittsburgh, developing high frequency magnetics for high frequency transformer. I started an effort a couple of years ago with Sandia, looking at high frequency inductors, passive components to support these applications. Ultimately, this is all being done to enable this power electronic power distribution, or PPEDS concept. And we have curriculum that's been developed, Anant Agarwal at Ohio State University, and he's delivered that curriculum, as far as I know, Ned, to yourself, and that curriculum is made available. Anybody who needs it and wants it on wide bandgap theory and application, again, through an ONR grant. Next slide, please. I mentioned IPEB. We started that effort in 2019, and that's going to be going to 2023. We shown there are some of the specifications on it. 1 kV to 1 kV. It uses 1.7 kV MOSFETs, 500 kilohertz switching frequency, 1/4 of a megawatt. And the key piece of this is the weight. The weight is 35 pounds, and that's important because the NAVSEA has specified that in order for a component to be able to be handled by one person, it has to be on the order of 35 pounds or less. Anything more than that, it requires 2 people to handle. So we're developing this IPEB with the goal, and it is currently meeting that goal of 35 pounds. Ravi, as I mentioned, is teaming with Virginia Tech in the development of the IPEB. But again, this is an area too with high frequency magnetics. That's an area of education that we need to make sure that people understand. It's not our grandfather's magnet anymore, but it's new magnetic materials that are needed to facilitate this high power and high frequency operation. Next slide, please. So let's get to the system level vision. We'll talk a little bit about PPEDs, NIPEC, and then the necessity for cyber secure physical systems. Next slide, please. So PPEDs, and I mentioned it previously, it's a concept of operation. It's a power electronic power distribution system. So on one side, you have sources. On the other side, you have loads. And then you have this onboard digital real-time control sort of in the middle that marries up with source converters and load converters. Shown there in the blue box for your reading pleasure are the sort of the construct there. No load or no sources directly connected to the bus. We're looking at generating AC, but distributing DC, but PPEDs will support either. It's voltage flavor agnostic. It'll support AC or DC. And think about them as power bots, IPEBs, programmed via downloadable apps. And that's why the cybersecurity becomes so much important, because we want to be able to make sure that this programming, this language, this code that gets downloaded into the IPEBs are secure and they're free from malware intrusion. Next slide, please. Some of the S&T gaps, and these are areas, you know, if you have ideas, please submit white papers, you know, on thermal. Dr. Mark Spector, and he and I have a STTR that is closing on thermal improvements for power converters. Insulation is always a gap. We want to be able to push corona inception voltage and partial discharge voltages higher as we go into higher dV by dt converters and drives. I've already mentioned high power frequency magnetics and wide bandgap semiconductors. Part of the PEB process is this module integration or these Navy IPEBs, stacking them together to form an actual system. Distributed control, distributed energy storage is where we're going next. We've done a lot with point of use energy storage with HESM hybrid energy storage module, and the Navy Electric Ships Office is focusing on delivering to the Navy Energy Magazine. Well, where we need to go next is to get to distributed energy storage. And then software design and development tools, S3D, for example, that has been developed by Kelly Cooper, and using those tools in conjunction with Asset and LEAPS to design our ships. If we use the tools that we use to design DDG 51 and hope to get something else in the future, we're not. So the tools need to be updated, as does the education that Dr. Mohan is doing, updating our education and making it available for our power engineers. Next slide, please. Navy Integrated Power Corridor. This is an effort that's sort of been a vision over the last couple of years. I'm starting that actually to start doing more than concept, starting to build. We're working with Julie Chalfant at the Massachusetts Institute of Technology through the ESRDC grant. And you know, the ships that I served on, cabling and shafting and power cabinets were scattered all over the ship. Imagine for a minute being able to have all of that equipment in a power corridor on the order of 20 to 25 megawatts, where you have your protection and your control, where you have your power conversion, where you have your cable and distribution, and all of that in these nice and neat in these cabinets. That'll free up the ship, a lot of payload traction for the ship to deliver whatever it needs to deliver for its particular mission. So this year, we're really kicking off hard in 2021, this integrated power and energy corridor with MIT and then with University of South Carolina, focusing in on some of the thermal management aspects in taking that heat that's from those IPEBs. And even though they're 99% efficient, there's still some inefficiency that needs to be dealt with. and removing that heat and putting that into the ship system. Next slide, please. Cyber physical systems, I mentioned a grant that I have with Dr. Mohammed at FIU. We need to develop cyber physical methodologies to protect these downloads, to ensure ship power system and minimize vulnerability, minimize cost, and optimize our system operations. This initial grant was initiated in 2017 or FY17 to develop a framework with which FIU had, through a DURIP, had developed a power system test bed. And we're investigating different security aspects of the hybrid physical system to ensure safe, malware-free, and secure system that's authenticatable to ensure programming and code is downloaded safely and securely to the power conversion and power distribution system. Next slide. Next slide. So now we're getting into some of the courses that ONR has funded through the years and the motivation behind that. A lot of our workforce is aged. I'm one who's also aged. It's been over 30 years, just about 30 years since I received my master's degree from the Naval Postgraduate School. A lot of the engineers at NAVSEA are in the same boat. And so we really need a better trained supply of US graduates in STEM, science, technology, engineering, and mathematics, to attack the various research challenges. And I mentioned many of them in my previous slides that the Navy is facing. We want to add flexibility and safety to ensure that they will be usable in these Navy courses. And they are being used. Naval Postgraduate School, United States Naval Academy, NSWC, Naval Surface Warfare Center in Philadelphia, are all using these courses to train engineers. And they're also using the courses to complement and supplement their curriculums at NPS and at USNA. And therefore, all the universities in providing a first-rate education to educate students in large numbers, hopefully we'll be able to hire in our workforces that have taken benefit from this, and it will continue to provide capability to our Navy and to our other services. Next slide, please. Shown here are a bunch of ONR grants going back to, I believe, Terry Erickson's first grant there back in 2006. And then a key grant, increasing electric power there, grant number 3, which ran from 2014 to 20, that established that energy engineering pipeline nationwide. And then there's a national dissemination of CUSP that's going to be completing this year. Dr. Gieselman at Texas Tech, and that is a certificate to be able to, for a master's degree that's being developed by TTU in conjunction with the University of Minnesota. And then lastly, Dr. Mohan is working on a 4-year grant developing wide bandgap based extremely low cost laboratories for power electronics, motor drives, and power system and protection. And that also will be for national dissemination and for use by those who are interested in power engineering. Next slide, please. A little bit on that STEM course from 2014 to 2016. It has its own name, EE 2701, Sustainable Electricity, Supply Renewables, and Conversion. And shown there are many of the aspects to include experimentation. It has been taught twice as of this slide. I'm sure it's up to 3 times now. Dr. Mohan, correct me if I'm wrong, but the course is being currently taught, and shown below are the various aspects in what is being taught and learned from that course in conjunction with the credit course, the laboratory, EE 2703, with those experiments that are shown there. Next slide, please. There's been 19 senior level graduate courses developed with, I believe, 54 credits, maybe 58 credits, but 19 senior level courses in power systems, power electronics, electric machines and drives, as well as renewable energy. And many of you are familiar or should be familiar with CUSP. And if you're not familiar, go to www.cusp.com to learn about that. program that Dr. Mohan has established in getting knowledge on power and energy out to our nation. Next slide. Some of the key challenges, again, that we're going forward that I mentioned earlier in courses that have been developed and have transitioned. The only one that really hasn't yet is the creepage and clearance. And that's a grant with Florida State, with University of Wisconsin at Milwaukee, and with Georgia Tech. And there's going to be another grant starting in 2022 to take this even further, focusing on PPEDs. As we understand in setting a standard for DC as well as AC systems, in particular the PPEDS application. Next slide, please. Part of not only learning the curriculum, but is also included in that is laboratories. And we need to be able to verify and validate, or V&V as we say in the Navy, hardware, going from simulation to the actual hardware. And Dr. Mohan has developed a GaN-based power electronics lab kit, as well as electric drives, 3-inverter lab kit. And shown there are, in the lower left corner, are a list of experiments tied to grid, tied to different components and systems, AC and DC, to be able to connect and run experiments. And the reason why he went to GaN is to be able to get the wide band gap and control authority that's needed to support the experiments. And then emulated power systems lab is currently under development, and a lot of work and a lot of progress is being made there in getting that fully developed. Next slide. So we talked a lot about technology. We talked a lot about courses, but the most important resource are the people. And shown here are the people at CUSP, and also at University of Minnesota, that have been supporting Dr. Mohan. I believe that the number as of June 2020, universities was 235. I believe that number is even higher now. We talked about disseminating this information to U.S. universities for classroom and distance learning. Some of the recent accomplishments include the 19 courses completed. There's just, I think, the one with the creepage and clearance that is coming next. I mentioned that these courses have been adopted by the Naval Academy, Naval Postgraduate School. Over 450 faculty members are using these courses. And then again, the far-term objectives is to train Navy and industry power engineering workforce with these emerging technologies that are, and a good sampling of those technologies I provided previously in the presentation. Next slide. Next slide. So in summary, I showed the motivation that warships, modern warships, have ever increasing demand for power dense power electronics, high power and energy requirements that are leading to an integrated power and energy system. The PEB S&T work I talked about, Navy IPEB, for example, a least replaceable unit, 35 pounds, being able to be handled by one person. A significant PEB progress has been achieved through silicon carbide power switching devices, and additional PEB improvements will be achieved and needed as we start integrating these PEBs together in a system, PPEDs. I mentioned there's a gap with high frequency magnetics. There's also a gap with thermal, and as well as insulation. So if you have ideas, white papers can be received in those areas that ultimately will lead to a proposal. But as I mentioned earlier, I do not have FY21 funding remaining, so we're looking at 22 or 23. Successful implementation of Navy IPEB into PEBs will be enabled through controls. So it's not just the materials, but controls is needed, both at the component and system level. Herb Ginn is working on those controls, looking at discrete energy packets, very similar to the communication industry in communication packets of information many years ago. We're looking at the same with energy, discretized energy. NIPEC offers innovative alternative to a traditional power and energy design. I talked about the tyranny of the shaft, of the cabling, of the cabinets, and hopefully this power and energy corridor will neatly provide an alternative and free up space payload fraction in space needed for the ship to perform its function safely and reliably. I talked a little bit about cyber physical systems and the need for those to safeguard power and energy systems and harden them against adversarial malware intrusion. I mentioned the FIU grant is a start in that area. And education, I believe, is needed in those areas as well in cybersecurity. But then lastly, none of the above vision can be brought to reality without power and energy sustainable focused curriculum that Dr. Mohan and others are working on in developing that curriculum. Again, people make the difference. Next slide, please. You can get in touch with ONR. We are on various social media sites, YouTube. You can see some of the work that ONR has done, Twitter, Flickr, onr.navy.mil. I'm on LinkedIn myself, and there's a lot that ONR is doing on LinkedIn. You'll be able, if you follow them, you can see a lot of their accomplishments and what they've done and what they're doing with industry as well as academia. So feel free to follow them on LinkedIn and stay up to date what ONR is doing. Next slide. And if there's time, I have a minute or two, I guess, for a couple of questions. Thank you, Dr. Mohan, for the time to talk to your team today at your workshop.
Yeah, thank you very much, Captain Peterson. It's very informative and very educational. And once again, I'd like to thank you for your continuing support. And also, as you mentioned, Terry Erickson is the one who got us started. And it was a kind of an uphill battle, as I understand, to support such a large educational grant. So I'm very thankful to ONR to keep us funded. And as you mentioned in the program in the agenda later on, we'll talk about these pipeline courses that you mentioned, because we need to draw in high school graduates to electrical engineering program. And today there's a lot of competition with computer science, and therefore it's really a challenge to kind of motivate them to come to electrical engineering, and particularly into power. And as you know, there's a great deal of need in transportation for sure, and also in the electric power sector, in your work in defense and Navy. So we will talk about our graduate courses that we have developed. Many of the developers are here in the agenda. They'll talk about it later on. And also, first and foremost is our lab development. So we are very excited about that. And our postdoc, Siddharth Raju, will talk about those labs. And of course, in electric machines and drives, and those are remotely controlled. So when the pandemic started in March last year, the course that we were teaching was in person on campus. But when we went to online, there was no disruption because those were all remotely controlled. And the same thing we're doing with Power Electronics Lab and with Power Systems Lab. And we are very excited about Power Systems Lab. We could have the whole tabletop microgrid, for example, for under $3,000. So that could be kind of a new paradigm in education and research in power systems. So we are extremely thankful for what you have done for us. And it'll be extremely gratifying to see all this development being used with all the universities nationwide and perhaps worldwide. So, again, thank you so much for being here and giving this enlightening presentation. And it looks like there's some couple of questions, Dan, for Captain Peterson.
Yeah, sure. Captain Peterson, do you see those questions, or would you like me to read them to you?
That's in the Q&A, right?
That's right.
Okay, so the first one I see is, besides basic course material mastery, what capability qualities as engineers are needed in graduates? And I think all of those that are listed there, you've got to be visionary. You have to be able to, as we say, think outside the bag that holds the box. Some people say you have to be able to think outside the box. Well, for ONR, you really, in science and technology, you really have to think outside the bag that holds the box. Creativity is important. Persistence. A lot of times with S&T, as we know, things fail, and a lot of people have developed master's thesis and PhD thesis when their project didn't fail, or when it failed, but really it's not a failure. It's because it's gaining information and knowledge, and if that information is disseminated, other people will not go down that same path because that knowledge has been gained that a particular path did not work. And so that's important as well. But persistence, patience, being determined, visionary, all of these are being able to, caring for your fellow workers. All of these are important attributes, skills, knowledges, and abilities that engineers need, not only in academia, but also in the workforce. And then there's a second question by Dr. Njetti. Hi, Dr. Njetti. Is the PPEDS concepts directed only towards Navy ships? Do you envision PPEDS disrupt? Right now, we're looking at it for Navy application, but I do see PPEDS disrupting traditional power distribution, in particular where power density, where you're limited in space to go forward, but also where your systems are going to be operating at higher frequencies. Some of the work that Herb Ginn is doing is in the nanoseconds. And he's developing these networks, 50 by 50 networks with less than 50 nanoseconds latency. And all of this is going to be needed to support that. So yes, it supports Navy ships, but it also could be disrupting in traditional power distribution. And I just had a meeting with GE. Don Hoffman invited me to a couple of weeks ago, where they're developing the HESM. And it was very encouraging to say that PEB, at least the concept of PEB, and the application of it is being welcomed and being implemented across industry. And so I hope that answers your question. Raja INR says, could you please mention the power and voltage levels of the LRU? So this particular level that we're looking at for Navy IPEB is on the order of 250 kilowatts. And it's a 1 kV to 1 kV DC to DC converter, the Navy IPEB, but it doesn't need to be that. PEB 6000 is a 6 kV to 1 kV DC to DC converter. And so those are some of the power and voltage levels that we're looking at. Ultimately, we're looking to getting to 20 kV distribution. And the reason why that number is important is because generators, we make generators at 13.8 kV AC. And so that's a nice rectification to 20 kV DC off of that AC generation. So I hope that answers your question there. And then Sastry, you're more than welcome. Always glad to see you and work with you and those from Florida State and the ESRDC. It says, please talk on the need for graduate programs in power engineering, given all the new technologies ever changing. I think I mentioned that in my brief. It says, I identified a lot of the applications that the Navy is looking at. The other services, Air Force and Army, are also looking at service pulsed applications as well. And there's going to be a need education that's being disseminated through CUSP and through the financial efforts of National Science Foundation, ONR, Department of Energy, and others are going to be very important as we go forward in developing graduate programs in power engineering. So I think that's it for all the questions.
All right, thank you very much, Captain Peterson. If any more questions come in, they may ask you directly, but if they contact me, I'll be certain to forward them to you.
Yeah, please do, Dr. Mohan, thank you.
Yeah, thank you. And please give my regards to Terry Erickson.
I will.
PM, because I can't thank him enough to get us started. It was such a, probably one of the most joyous occasions in my professional life to get that grant from Terry Erickson. So thank you again. And so we move forward with our agenda. We have a pretty exciting agenda.
Thank you. Have a great day, everybody.
Okay, thank you. Okay, so let's move on. Our next presentation is on these pipeline courses that we have developed. And so the first course is 1701, we call it EE 1701. And my colleague, Professor Bill Robbins, he will describe that course. So he is a faculty coordinator for that course with high schools. And a very brief introduction of Professor Robbins. He's probably the longest serving faculty member in our department. I have been at the University of Minnesota for 45 years, and I think he was there probably for 4 or 5 years before I started. So it must be 50 years, Bill, that you have been in our department. So he has a very distinguished career. He was our associate department head, and he has been very kind to join this power effort that we have, especially looking at semiconductor device physics. And so what he's going to describe to you is this first pipeline course that we are very excited about. So Bill, with that brief introduction, if you could, tell us what you have to tell us.
Okay, I presume that I can share my screen. Yes, okay. Okay, hopefully you can see my first slide. I'll talk today about the course entitled Climate Crisis Implementing Solutions. We go by the course name here, EE 1701, and accompanying lab EE 1703. I'll talk about the lecture and lab courses in terms of the outline that we follow in general. Then I'll give some examples of the course content, and then talk about the available resources for teachers, both at universities or at especially at high schools. And then briefly talk about the College in the Schools dual enrollment program, which is the vehicle that local high schools are using to be able to teach this course at their local high schools. Okay, the outline for the course is shown on this slide. The topic and some of the details of each topic, and the approximate semester hours that we follow. And we first talk about climate change. What is the evidence, the causes, the consequences? And then we give an overview of a mitigation strategy in which we use renewable electricity to replace fossil fuels. And then to get further into details, we talk about conventional electricity sources, fossil fuels, nuclear, hydroelectric. And then we spend quite a bit of our time talking about electricity from renewables, that is wind, solar, hydroelectric, biofuels. And inevitably, we have to talk a little bit about the power grid, because you can't talk about just generating electricity. You have to talk about the power grid, what the structure is, the components, operation, and especially the need for energy storage when you're talking about interfacing the grid with renewables. And then some of the other issues that or topics I should say, that we cover are conservation, that is lighting, such as going to LEDs, making electric motors more efficient, agriculture more efficient, heating and air conditioning, and especially transportation. And then where appropriate, and we have the time, we talk about energy policy. That includes subsidies, carbon tax, grid management, net zero metering, and other topics. And finally, try to summarize all of that by saying that what we need to inculcate in our students is a sustainability mindset, and then, of course, the need for action. Accompanying this course is, let's see, I guess I'll have to go up here, is the EE 1703 course. This is a 1-credit course, laboratory course. It's optional for university students, and it satisfies part of the physical science theme that's required for graduation at the U of M, particularly for non-engineering and non-physical science majors. In high schools, this course is combined with EE 1701 as a combined 4-credit course. And here I have a list of the experiments and demos that we do. We have an experiment on the greenhouse effect, where we demonstrate what the effect of CO2 is in terms of heating and cooling compared to just normal atmosphere. We do a couple of weeks on solar cells. We do the IV curve measurements, maximum power point, and then we talk about various panel combinations and connections. We have an experiment on rooftop solar, which is mostly on talking about the arrangements and some calculators that we like to use for students to get more acquainted with how much power they can get at a given time of day and so on. We talk about community solar. We have an experiment on wind energy using a lab scale wind turbine, and we actually measure the maximum power point. We have an experiment on lighting technologies where we compare incandescent with LEDs and compact fluorescence. We have demos on point of use water heaters and some calculations, air conditioning and heat pumps. We have a speaker who is very good, who comes in and gets students all enthused about electric vehicles, and then some efficiency and cost analysis using a calculator. We talk about AC systems, real and reactive power. That's part of our discussion of the grid. We have a week on motors and generators, and a semester-long project on growing plants using LEDs and automated watering. So this gives you some idea of the topical things that we cover. As far as the other curriculum details, for U of M students, this is a freshman level course. All they need to do is be enrolled at UMN at the University of Minnesota and want to take the course. For high school students, they get enrolled through the College in the Schools program, which is a dual enrollment program. The prerequisites for the high school students is completion of a high school physics, chemistry, or biology course, or an environmentally related course with a grade of B or better. At the U of M, it's usually 3 contact hours per week for a 15-week semester, or 2 75-minute lectures. For high schools, it's 4 to 5 periods per week for the entire academic year. The length of these periods varies from one school to another. Some may be as short as 35 or 40 minutes, some upwards of 50 minutes to an hour. And while at least one high school has tried it for just an academic semester, the teacher said that from then on, she wants to do it for the entire academic year. All the other schools that have tried this are doing it for the entire academic year. As far as instructional materials, there's no text at present, but we're trying to develop a free downloadable digital text. We have loads of PowerPoint slides. It's probably well over the 300 that's listed here. We have various videos, papers, and simulations and other simulation materials that's available. And we have the hardware demonstrations, lab manual write-ups for the various experiments. And we also have lists of equipment, where to get it, and how much it costs to outfit a laboratory for most of the experiments in a high school, something on the order of $3,000 to $3,500, I think, at present. As far as grading, the course is based 25% on weekly or bi-weekly homework assignments. These are usually numerical and descriptive and qualitative problems, 2 midterm exams, 20% each, and a final exam. And the students in the high schools do exactly the same work or very similar work to what the university students are doing. They take the same exams or very similar exams, including the final exam. As far as examples of what the course content is, here is a summary slide of electricity as a possible solution to combat climate change. We talk about the sources and usage of electricity, the possibilities of shifting energy use from fossil fuel to renewable-based electricity, and we talk about an overview of the current generation technologies and ongoing research. And I have a couple of inserts here that show the U.S. energy primary consumption by economic sectors and the current generation mix as of about 2015, I guess. When we get into specialized or more detailed discussion, we talk about hydroelectric generation, for example, including conventional dams and run-of-the-river hydro plants. We have both the lecture material and the experiment on wind energy, and we talk about the fundamentals, including Betz's law, the structure and efficiency of turbines, comparison of cost comparison with wind electricity and other sources, the challenges to the grid, and we talk briefly about the wind forecasting and day ahead and near-term markets, and talk about success examples. We talk quite a bit about solar photovoltaics, and I've listed some of the things that are talked about in the course of discussing these, including the cost of just the cells and the balance of system, comparison with PVs versus other sources of electricity, and what the effect of the variability of solar generation is on the grid, and examples of success in Hawaii and California, for example. And of course, we want to talk about the need for energy storage, brought about by, I think it's termed the duck curve, where the load is highest in the early morning and late or in the evening, whereas wind energy peaks in the night and solar energy peaks at noon. Various types of storage are talked about: batteries, pumped hydro, compressed air, flywheels, thermal storage. I even saw a recent article where they develop so-called gravity-driven. Well, pumped hydro is gravity-driven, but this one was they lift very large weights a short distance, and then it can be placed anywhere. It looks like they use some kind of tower crane to lift it, and then they let it down, pulling on a generator, and when the power is needed. For example, there's a vanadium redox flow battery that's being put into service in China that stores 800 megawatt hours of energy. Conservation and efficiency is talked about, including using LEDs, replacing constant speed electric motors with variable speed drives, air conditioning choices such as heat pumps, and conservation in the agriculture sector. And examples of this would be using EVs and recharging them by renewables. And of course, upgrading our residences, hopefully some being up to so-called LEED standard housing. I won't get into the details of that right now. All right, some of the course resources. At present, we have no text, but we have a free downloadable digital text is planned. We have a large number of PowerPoint lecture slides, homework assignments, concept quizzes, exams, and this includes solutions as well as the exams and homework assignments themselves. We have links to supplementary materials of all kinds. We have recordings of invited speakers. We have hardware demos and lab manuals for the experiments. We have lists of the equipment, including the sources where you can buy it and what the prices are. And the development of new experiments is ongoing. I am the designated university faculty coordinator between the university and the high schools, and I'm available for high school teachers to ask questions who are teaching the course, or from high school teachers that have heard about the course and want to know more details. We also have the cohort members, that is the high school teachers who are currently teaching the course. And every semester we have a professional development workshop for all of the current high school teachers. And this includes one in the summer. And here I show a couple of examples of what's available. A picture of our laboratory scale wind turbine. We have a number of small solar panels and places where high schools can go to buy them if they want, and an example of one of our experiments where we do a series parallel connection of 4 solar cells. I thought I would end briefly by talking about what this dual enrollment program is. Dual enrollment programs are nationwide, and they are accredited by a agency called NACEP, which I think is National Accreditation Consortium or for Concurrent Enrollment Programs. And in fact, our program was just recently accredited again for 6 years. The course is taught by high schools, or taught by high school teachers in the high schools. The student gets credit toward high school graduation and also receives University of Minnesota credit, which can be transferred to other universities. High school students perform the same or similar work to U of M students and are graded to the same standard. As far as what the high school teacher requirements are here in Minnesota, they must have, of course, a valid Minnesota teaching license and a minimum of 3 years teaching high school juniors and seniors in STEM or environmentally related courses. They need a general knowledge of the topics, and they also need to demonstrate advanced related content knowledge. This could be done by a graduate degree in STEM, or there are other approved methods that I won't get into, such as a graduate degree in some other field, plus lots of experience in the area. And I won't get into, there's a number of different ways that they can demonstrate advanced knowledge. The cost to high schools is approximately $150 per student paid to the university. And the cost of instructional materials is paid by the high school. The role of coordinator is listed here. I'm a resource and point of contact. I interview potential teachers with the CIS staff. I conduct the professional development workshops, mentor teachers. I'm a liaison between the college and the schools program and the double E department. Current status of our high schools who teach the course, there's 3 teaching it right now. 2 schools have taught it in the past, but not this year, primarily for various reasons, including in one case, a teacher who was going to teach it transferred to another school during the summer. Teachers have been approved by CIS in several other schools, but these schools at the last minute canceled the course before classes started, again for various reasons, including teacher reassignments, change in programmatic thrusts, and so on. So I think that will be the end of my slides. I'll be glad to answer any questions that you may have. Let's see, there's a couple of questions. Let me bring that up. Okay, one is, what's the logic behind the series parallel? Isn't the current still limited by the single path? The answer is this is just one of several different variations. I just brought up an arbitrary one to show, because among other things that we wanted to show the bypass diodes, which are necessary in order to provide a current path in case one particular cell or panel is shaded or starts to fail. This is not an AP course. For those who are unfamiliar with the terminology, AP means advanced placement. And will other universities accept the credit if the high school students attend other universities? The answer is that will be up to the university to which the student is trying to get the credits transferred. But the students receive University of Minnesota credit for taking this course, like any other University of Minnesota course. And so if the students are trying to transfer their course, it will be up to the individual university they're applying at to make that decision. I might say a couple other words about AP and IB courses. IB stands for International Baccalaureate, and there's also post-secondary enrollment options. And the high schools themselves, particularly the teachers, prefer the dual enrollment because the students stay on campus. In the post-secondary enrollment option, for example, the best students who enroll in that have to go off campus, off the high school campus, and aren't there part of the day. And so the high school teachers, as the language they use is, they're losing some of their high flyers, which sometimes motivate the rest of the class. And the AP course, I think, is considerably more expensive than the dual enrollment course. And I'm not that familiar with what the costs are for the International Baccalaureate. There is a separate site for the course that we're talking about here, but I'm not sure. Ned will have to answer the question about, are we going to post it on the CUSP website? I don't see any reason why we couldn't. Yep. Is there a way to do the lab remotely, or does it need to be hands-on to be successful? Well, right now this lab is not remotely doable. And in fact, we encourage as much as possible the students to come in. For example, I'm familiar with several of our undergraduate laboratories in electrical engineering. And even in the day of COVID right now, we are doing it face-to-face because we are using social distancing, and everyone has to wear masks. We did it in the fall semester successfully, and so far in the spring, it's working out quite well at the university. Each high school who has this program will have to determine for themselves if it's going to be remote or not. At least some of the experiments, which are mainly demonstration and use of calculators, probably can be done remotely. As far as some of the others, one way of doing it is the instructor sort of does the experiment while the students watch via Zoom, and then he sends the students the data from the experiment, and then they have to write a lab report on it. We've used that format even at the university for a couple of our laboratories when we had to, on short notice in the middle of the semester, convert from face-to-face to remote during the spring of last year. I think that answers most of the questions so far.
Yep. Well, thank you very much, Bill, for a very complete description.
Okay, one more came in. Do the students work in teams, or each student do his own? I think they work in teams. I know in the high schools, the high school teachers encourage them to work in teams. And most of the high school teachers that I've interacted with say it's necessary to have the lab because high school students have somewhat of a limited attention span, and the use of the labs interspersed with lectures is the way to go because they get much more interested in doing hands-on experimentation than listening passively to a lecture.
Okay.
Okay, right, I think Bill, that probably ought to do it.
Yeah. Thank you very much, Bill.
Much for attention.
Yeah, very, very complete description. If I may just add a few things, that this course has been quite popular. We had as many as 110 students enrolled because this is a university-wide course. It doesn't have any prerequisites. So it has the possibility of enrolling a lot more students. And as Bill, you mentioned that it's being adopted in 5 schools. And Minnesota alone has 500 schools. So there's a lot farther to go. And this course could be taught by various schools, various universities in every state. And Minnesota is an average sized state. So if you multiply by 50, these 500 schools, you end up with 25,000 schools, okay? And even if just 5% of them adopt this course, we're talking about, over 1,000 schools, okay? So that could be a pretty good pipeline for us to bring those students into electrical engineering if we can, train them properly. So, that's just my brief comments and, in connection with an elaboration of what you have presented, Bill. So thank you again very much. And I will just continue on with the second course that we have. So let me see how I can do that. I could go to share screen, and hopefully I could bring this PowerPoint slide. I have just a few slides here, and this is my, okay. All right, so the second course that we have is this EE 2701, and it's titled Sustainable Electricity Supply, Renewables and Conservation. So again, this course doesn't have any prerequisites now. It's also authorized to teach online, just like the previous course that Bill described can be taught. In fact, the lab in the previous course 1703 can be taught online. It has been authorized to be taught online, except the experiments we have today in 1703 are not, cannot be done remotely. So we are working on it, and hopefully we get there. And all the material, there was a question, all the material we developed for that previous course that Bill talked about would be available free of cost to anybody who is interested. So as soon as that's done, whether it's posted on CUSP or that course has its own website, the bottom line is that that material would be available free of cost for educational purposes. So very briefly, this course that we have, Sustainable Electricity Supply, this course is, could be taken by anybody, but primarily is designed for engineering students, not necessarily electrical engineers. And because a lot of the things that we talk about apply to other engineering branches. So anything that is needed as the background we cover in this course. So let's see if I can go to the next slide. So here the syllabus. So we start with motivation and the role of electrical engineering in accomplishing that sustainable electricity supply. We talk about basic electrical engineering concepts like review of AC and DC analysis and time domain. And if they haven't taken it, that's okay. We talk about it from scratch. Then we talk about phasors for steady state analysis and three-phase balanced circuits. So all of them, we do it in a very, upper level basis without getting into too much nitty-gritty of things. And then traditional sources of generating electricity, which can be replaced by renewables, and then role of power electronics. So you can see that there's quite a bit of difference between this course and the previous course that Bill talked about, because this is definitely electrical engineering oriented. And we have a senior level course in power electronics, but a lot of people may not go into the power power option. So this course gives them a pretty good overview of power electronics and electric machines and drives, power systems, and then we integrate all those in different applications here. So that's basically the outline of this course. And again, we are developing material for this. And also there's a lab that would consist of what we have done for our senior level courses that next presenter, Dr. Siddharth Raju, would present. So again, everything we do in this course would be disseminated and hopefully you can make use of it. And this again can be a very popular course, although we do not wish to promote it into high schools because I think it'll be too much. So just the first course that Bill talked about is the one which is for is applicable to high schools. So I'll finish with this, and I'll stop sharing here. And it looks like there are no questions. So I'll move on to the next one, and that is about the labs. So let me go to screen share here again, and click on share. Okay, and then close this PowerPoint here. Okay, and then I'll just introduce our next session, which is on laboratories, and then I'll let our postdoc Siddharth Raju take over. So let me just go to the labs here. So I hope you're seeing my screen, and so these are just a few introductory slides I have before I turn it over to Siddharth. Okay. So these are the ONR funded laboratory development that we are going to talk about. There's electric drives lab, there's a power electronics lab, This power systems lab is under development, and then power electronics and power systems. There's high power electronics. So we are very excited about that, and we will be doing it this summer. So very briefly about these labs without going to the details. So a little bit of history that we started developing these labs, I think more than 15 years ago, and 109 US universities in the past have acquired these labs. So that was very gratifying. But it's time to develop new labs for a simple reason that after 15 years, these some of the components don't work, and these legacy components are not available. So that's the rationale for developing these new labs, and they need to be made state of the art. So in these new labs that we are developing or have developed recently, they use these wide bandgap devices. They are digitally controlled. The previous labs were controlled by analog means, and then they are remotely accessible. So that's another thing, is that it doesn't have to be taught online, but if you need to teach it online, for example, if you have an online global campus, you can very easily teach laboratories through to the internet remotely. So that's always a question, that if you're teaching online, you can of course teach lecture courses, but what do you do for the labs? Okay, so here, by making them remotely accessible, we overcome that challenge. And the next thing is that much lower cost. So as Siddharth will describe, these labs are a factor of 5 cheaper. Okay, so most universities, perhaps all universities, can afford to have such labs. And if you decide to teach online, then only one setup is needed, because you could have a timesheet where a student can sign up, and only one setup is needed instead of 4 or 5. So it makes these labs cheaper by another factor of 5. So that's quite exciting. And then we are keeping them at 40 volts and low power. So that way we can not only overcome the cost issues, but also keeping it very safe, because the whole intent is for students to learn the basic concepts rather than worrying about safety, although we emphasize safety, saying that think about this as a high voltage and high power. What do you need to do? So, they have to sign something they understand about safety, even at 40 volts. Okay, so that's really our rationale. And then I mentioned to you this lab for high power electronics. We have a course, Power Electronics and Power Systems. So in conjunction with that course, we are developing all these experiments that you see listed here, quite often used in high power electronics. For example, these multi-level converters, multi-modular converter, MMCs, and then Captain Peterson talked about this high frequency transformer design. We will have a software-based lab using this ANSYS program, but it could be any other finite element analysis program, and also how to implement WBG devices. So these are some of the experiments we are going to develop this summer. We have a student who is going to work 40 hours per week for us, and hopefully we complete this all. And as soon as it's done, it will again be disseminated. And we're very fortunate that there is a University of Minnesota startup called Sciamble, and all these laboratory kits are and will be available through this startup. And I have no financial or zero financial interest, and I purposely kept it that way, so there will be no conflict of interest. So with that brief introduction, Siddharth, I will stop sharing. And so the stage is really yours. So just to briefly introduce Siddharth. Siddharth came here to do his master's and then PhD. And he did it on matrix converters. And but in the process, he has developed something what I call amazing, which is software, which is very much look alike to MATLAB Simulink. So it's very easy to use, and it can seamlessly control these hardware laboratories that he is going to describe to us. So with that introduction, Siddharth, let me see, there's one question here, if it's for me. Are these lab experiments operating at low voltage? That is correct. That is correct. Prasad, as I mentioned, that all these things that we are developing are at low voltage of 40 volts. So they are very safe. They are very safe. We purposely kept it at 40 volts, even though we talk about high power electronics, for example, that will be used at very high voltages like HVDC. You're talking about plus minus 400 kV or even higher. But the concepts are the same. So we are keeping it at a very low voltage. All right, so with that, so that stage is really yours. You just, take it from here.
Thank you, Professor. Can you hear me?
Yep.
All right, let me go ahead and share my screen. Okay, thank you, Professor. And today I'll be talking about some of the hardware labs that we have developed, and some of them we have made available, and the rest of them should be available by end of this year. And we have a couple of interesting labs, 4 set of labs that I'll go over in this session. So here's the outline for this presentation. I'll be talking briefly about the software that we design in-house called Workbench. And then I'll talk about the electric drives lab, both the basic, which is the undergraduate level lab, and the advanced drives lab, which is for graduate level courses. And this lab is now currently available, and we have offered it the last 3 years for the basic drive lab and last 2 years for the advanced drive lab. And after that, I'll talk about the silicon carbide plus, GaN plus silicon based power electronics lab that we have developed. And we are going to make these labs available in our own university as well as other test universities to do a beta test starting this summer. And the third lab is our power system lab, which is again GaN based. That is the most exciting development that we have because it lets us emulate pretty much everything else that we are developing. And it's a tabletop setup, which can emulate any number of nodes of a power system. And finally, I'll talk about a general purpose controller that we have developed so that the labs that we are using can be extended for research as well and not just stop with teaching alone. Okay, so before I dive into the software and the hardware that we developed, I just want to briefly talk about the motivation as to why we went in this direction. As Professor Mohan had mentioned earlier, these labs have been developed by Professor Mohan and adopted by multiple universities under the CUSP group and over the past 15 years. And one of the first labs that were offered was the power electronics lab, which was followed by the electric drives lab, which was offered in, I think, around 2007, 2008. And it has been used for over 10 years. And as Professor mentioned, a lot of these components have become obsolete. And so we had to update most of these hardware. And while we were updating the hardware, we heard from a lot of people who said these labs were really expensive because of the controller we used and the software we used. And even though most of us take MATLAB Simulink for granted in universities, these are quite unaffordable in startups as well as in universities in developing countries, as well as technical community colleges here in US. So we wanted to remove all of these components that we were dependent on earlier and replace them with newer components. So here's the cost breakdown currently for the older version of the lab. Again, as I mentioned, MATLAB we take for granted. Most universities have university-wide license, but they do tend up being pretty expensive in the academic version with all the toolboxes needed to run embedded motor controls. It does end up adding a lot of cost. So per station previously used to cost about somewhere between $10,000 to $20,000 for the academic, and non-academic versions are way more expensive. So that was the motivation to bring down the cost down as much as possible so that we can extend the reach of these labs to as many universities as well as practicing engineers. And with that aim, the first step was to remove the dependence on MATLAB Simulink because of the cost involved. So we developed our own numerical simulation and rapid prototyping platform. And as Professor Mohan mentioned, it's similar to other model-based design platforms such as MATLAB, Plex, and PSIM. So it's very similar in that if you know one of those platforms, you should feel quite comfortable starting with Workbench. So you can drag and drop any number of toolboxes and connect them, and you can build a model. And it has a programming language as well, and it has almost all the features that you would need to implement any kind of motor controls as well as power electronic real-time control. It has an advanced coding environment, and it has inbuilt support for all matrix operations. So here's the overall screen grab of the software, and we'll go over the system. I'll show a demonstration of the lab running this particular system shown here. And over here we have the induction motor vector control model. On the top, you have the induction motor model, and on the bottom, you have a DC motor to emulate a load connected to an induction motor for laboratory testing. And all of this model is simulated in Workbench and also run in real time on a three inverter hardware that I'll be showing later. Okay, so here are some of the features of the Workbench software. It has, as I mentioned earlier, a programming language which was designed from scratch, and it supports dynamic compilation. So what that basically means is as the user keeps writing the program, the software compiles it in the backend, and as you make any mistakes, you immediately get those errors reported to you. We wanted to have this kind of advantage because most of the time when we were doing these labs and using MATLAB, we always used to encounter the problem where the students develop a significant amount of the lab, the model, and the code involved in the M file. And then when they hit run, they get a single error at a time. And it kind of starts being frustrating, debugging each of these errors at a time. So we wanted to make sure that as and when the error is made, like while the typing, while the design is happening, it gets reported and rectified rather than having to do it one by one at the end at runtime. So the language is extremely easy to use. As you can see on the left, it's pretty much like typing in English. And if you're familiar with any programming language, C or Python or JavaScript, any of them, this should be rather straightforward. And it has inbuilt matrix operation, as I mentioned earlier. So the most interesting feature that we have in Workbench is the ability to do both simulation as well as real-time control using a single model. So again, when we used to use MATLAB DSpace, we had the issue of having to have two separate models being developed, one for simulation, where the students develop a motor model and then simulate the system. And then they go to hardware, they need to create a separate model using DSpace toolboxes and then have control desks for data logging. So this two-step process kind of removed the connection between the hardware and the software. And that led to certain problems like when there wasn't sufficient sampling rate, or if say your duty cycle gets clamped off at 0 and 1, or your ADC has some sample time, those kind of non-linearities are not reflected in while you do your simulation. So the problem is that those things that could make it unstable, say the limits of the PA controller, the limits of your ADCs and PWM, say they set up some limit cycles in your real-time environment, those do not reflect in simulation because you had two separate models. So we wanted to remove that. Whatever happens in hardware, we wanted to be able to port it to the software as well. So if your ADC is going to saturate in hardware, we wanted that to be reflected in the simulation as well, so that you can take action in simulation state before going to real time. Okay, so here's the overall screen grab that I showed earlier. On the top, we have the induction motor model. So let me briefly go over the model before I show you the feature. So on the subsystem label here, IM motor, inside it is basically the DQ model of an induction motor. And on the left of it, we have the PWM blocks, which basically convert the voltage reference, voltage being fed into the motor model into duty cycles, so that the actual hardware inverter can then turn on and turn off the switches to generate the desired voltage. And on the left of that, we have the inner current PA controller. And to the left of it, we have the outer loop speed controller. And we have the estimator model on the top, which basically measures the current and the speed and estimates the rotor position, so that we can align our DQ axis along the rotor flux linkage. And on the bottom, we have a DC motor. So our setup usually has two motors, one acting as a motor and another one acting as a generator, basically a load. And the DC motor emulates a step load. So it's simply under current control. with a step-up light for torque. So when we do simulation, all of these models, the PWM and the ADC models, they just act as a 1:1 block. So whatever is in the input gets reflected in the output, and all it does is add its properties of nonlinearity. So say if your duty cycle goes above 1, your PWM block is going to clamp it off. And say if your ADC sampling rate, it's going to have, say, 3 million samples, say, or if it's going to have 1 microsecond sample rate, then if your input is, if your step time is much lower, your model step time is much lower than 1 microsecond, your ADC is going to automatically sample it at only every 1 microsecond. So those are the nonlinearities that get introduced. But other than that, it's just a 1:1 block. So when you run the model, you just simulate the whole model as you would in any other platform like MATLAB or Plexum or PSIM. And when you go to hardware mode, all you have to do is click on this button on the top right next to the run button, and the software will automatically figure out what component needs to get programmed in the real-time controller to run it in an actual hardware, as opposed to components that just needs to be in the simulation. So as you can see here, once I went to the hardware mode, the software automatically identifies that the induction motor and the DC motor are no longer needed to be programmed in real time, because we have an actual induction motor and an actual DC motor. So these component gets grayed out. That basically means the software is not going to code them in the real-time platform. So this kind of intelligent algorithm that we have developed in the background basically allows the user not to worry about any kind of demarcation between what needs to go in hardware or software, because it's automatically figured out and taken care on its own. Okay, as I mentioned, the software automatically identifies, and this leads to extremely optimized code because only what needs to run into the hardware is getting programmed. And we also have like a lot of optimization in the back for all the libraries that are developed. We have written them in assembly so that you can push in as much of control algorithms into your real-time controller. So the other aspect about the Workbench is we wanted to have the same features that we had with DSpace, which was like extremely friendly device settings. So if those of you who have used MATLAB Embedded Coder must be familiar with the difficulty of having to know about the device that you're using. So you need to know about the device register. So if you want to configure a PWM, for example, in a TI microcontroller, it's about 20 pages of registers that you need to know before you can set a single duty cycle at the output. And that takes a lot of effort, and it's not productive for your students because the objective here is to not teach them embedded programming, but to teach them motor control. And so we wanted to make these settings as device agnostic as possible, so that students no need to have any prerequisite of programming knowledge of any device or any programming, C programming or those things. So as you can see here on the left, if you want to set a PWM frequency of 6,000 or any PWM frequency, select some sample rate for the ADC. It's just simple settings, and the software automatically translates to device-specific register settings in the backend. So that's pretty much it. And so before I go into the hardware demonstration, which I have pre-recorded and I'll be showing you, here's the new lab that we developed, which we have been offering for 2 years now. So we have the Workbench software, which we use to replace the control desk platform for real-time control, and the Workbench MATLAB for simulation, as well as MATLAB real-time workshop for real-time code conversion. So all of those 3 platforms, we combined it, and made our own in-house platform called Workbench that can be used to program, that can be used to simulate as well as generate real-time code and program it and get all the software, all the data back logged into the software. And we revised our old inverter module and we made it much more compact, about 1/3 the size. And we reduced the cost significantly. So previously it used to cost with the motor and the inverters about $7,000, and now the motor inverter all combined is about $3,000. So here was the previous cost breakdown that we had, and this is the new cost. So it's about $3,000, which previously used to cost about $20,000, including when you consider MATLAB's cost as well. Okay, so in the next slide, before that, let me just, there's a couple of questions. Is Workbench based on Python, Professor NGT? Professor, this is based on C#. We use .NET platform, and it's based purely on C#. Do you have any specifications for motors and the 3 inverter circuits? So that'll be in the next slide. I will just be going to the next slide. So here's the whole lab kit that we have. We have the 3 inverter module, and then we have 2 DC motors. So for one of them in the labs, you usually start off with the basic device lab starts with a DC motor parameter estimation and then goes to DC motor speed control. When we do the DC motor speed control, we have one of the motors in speed control mode. And as I mentioned earlier, we always have 2 motors, and the other motor acts as a generator, which emulates a load. And then we have the permanent magnet synchronous motor. So we have the surface permanent magnet synchronous motor. We are working on designing and developing an interior permanent magnet as well, so that we can add an experiment in the advanced electrical drives lab. And we have a low voltage induction motor. So the induction motor is again low voltage, low current, and we are working on getting it's a single squirrel cage induction motor, and we are working on designing a low voltage doubly fed induction motor as well. Okay, so here's the specs of the inverter. It's a 40 volt 40 volt DC bus rated inverter, and it has 3 phase inverters on it. So we have 3 inverters because to control a DFIG with a coupled load emulator, you would have stator control, which is one of those inverters, and then the rotor control, which is the other inverter, and then a coupled motor, coupled generator to be emulated. We have another inverter. And all of these inverters are rated 10 ampere, but we have limited the current to 5 amperes because all the motors that we have are rated somewhere between, depending on the motor, it's between 3 ampere to 5 amperes. So each of these inverters is hardware limited to about 5 ampere. But if needed, we can just change a couple of resistors and extend it to about 10 amperes. And it has all the sensors on board, all the current sensors, and as well as the speed sensor, position encoder sensor on board. So it's a completely self-contained system. And it has an onboard TI DSP as well, which can be directly programmed from Workbench, and it does not need any additional third-party software. It does not even need Code Composer Studio, which is the TI platform for programming, because the Workbench software automatically generates assembly code and flashes the device. So you don't need to have any programming knowledge or need to be familiar with any third-party environment. And the system connects to standard USB 2.0 cable. So you can just connect it to your computer and directly program it from there. So again, but we have no specs on the components. So again, here's the specs that you had asked in the questions. And there's the specs again on the Cyamble website. So if you go to cyamble.com, okay. So on the resources section, basic drives, introduction. So we have the whole lab manual listed on Cyamble website. And once again, this is listed in cusp.umn.edu. So if you go to the courses, power electronics, electric machines and drives, on the bottom, you have the whole lab course. Again, from here, you can go to the lab manual from the CUSP website and basically lands here. And here you have the complete specs for each of the motors and the generators and the 3 inverter module all listed here. We have another question. What happens if there is an overcurrent condition? So if there's an overcurrent, nothing should happen. We do have inductors on the output, very small ones, which basically limit the short circuit current, the rise of the short circuit current, so that the inverter hardware can kind of detect the short circuit and take action. So if the students can literally just short 2 of the output phases in, the inverter would still be protected by the hardware fault. And in addition to the hardware fault, there is a software protection, interrupt triggered, as well as software runtime protection. So there are multiple stages of protection. And if one of them fails, the other one will take over and kind of shut down the experiment so that the inverter is still protected. There's another question. Could we independently use Workbench generated code to other microcontrollers? So right now it is, so we do have an option to generate code, just a generic C code without any device specific setting. And it's a readable C code that's generated. So you can take that C code and then set whatever device register that you want for your particular device and use it with that microcontroller. But for device specific code, we only support TI microcontroller, that too, especially the Delfino and Piccolo series. Okay. So here's the list of experiments. and that we have already developed the lab manual. As I mentioned, the lab manual is available here. So the website is still under development. There's still a lot needs to be developed, but the software, the lab manual for basic and advanced electric drives lab is complete. So we have a total of 8 experiments in the basic drives lab. And those are listed here with the introduction. And then in the advanced electric drives lab, we have 7 experiments. So this is for graduate level course, and the basic drives lab is for undergraduate level course. And as I mentioned earlier, we have offered the drives lab for about 3 years now. This is the 3rd year ongoing, and this year and the last year it's been remotely offered. And the advanced electric drives, depending on the enrollment, we offer it sometimes and sometimes we don't. So right now we offer it just once, the advanced electric drive lab. So here is a pre-recorded video that I have for the advanced electric, one of the experiments in the advanced electric drive lab, which is the induction motor vector control. And as I mentioned earlier, this is the induction motor model, where on the top we have the induction motor and on the bottom DC motor. And we have the PWM control here for the induction motor, and similarly PWM control for the DC motor. And then we have the DQ to ABC conversion. And before that, we have the inner current control and the outer speed control. And on the right, we have the ADCs to measure the actual motor currents, which are used in the estimator model to estimate the induction motor rotor flux linkage position, so that we can align our DQ axis along it. And on the bottom, we have the DC motor to emulate load torque. So here's the overall model, and we have all the parameters initialized in the script file, as I mentioned earlier. So all the PI values that are computed and all of those are written in the script file, which initialize all of these toolboxes. And it's similar to what you would get with an M file. Okay, so let's. I'm sorry. I just heard from Jam, my colleague, that the audio is not being played. Just a second. Jairam, can you hear the audio now? I'm sorry about that. My computer audio wasn't shared. I hope you can hear the audio now. So let's go ahead and run this in real time. And you should see the motor spinning. And let me open up the speed scope as well. Okay. So let me stop that and run it again for those of you who have missed it. But let me just go over the results before doing that. So at 1 second, we have a step in the current, a step in the speed, reference step. So if you look at here, we had a step of at 1 second, we give a reference step of 100 radians per second. And at, I think, 3 seconds, yeah, at 3 seconds, we load the induction. So let's go ahead and run this in real time. Okay, looks like my so let's go ahead and run this in real time. Sorry about that. And you should see the motor spinning. And let me open up the speed scope as well. Okay. So let me stop that and run it again for those of you who have missed it. But let me just go over the results before doing that. So at 1 second, we have a step in the current, a step in the speed, reference step. So if you look at here, we had a step of at 1 second, we give a reference step of 100 radians per second. And at, I think, 3 seconds, yeah, at 3 seconds, we load the induction motor with the load torque. So you can see at 1 second, the motor starts to accelerate and settle down at the desired speed. And at 3 seconds, when you add a load, there's a small dip in the speed, but the PA controller recovers and increases the voltage applied so that the current is more, and it cancels out the load torque so that the speed settles back again. And here's the ID IQ values. This is the ID and IQ values. There's a bunch of noise on the scope because I set the frequency pretty low at 12 kilohertz. If you increase the 12 kilohertz to 24 or something, this ripple content would be much lower. And yeah, so we see the ID current, which is constant at 1.2, which maintains the induction motor flux. And the IQ current, you see an initial spike because the motor is initially accelerating. And once the motor settles down, the current will be almost zero. Only the frictional component needs to be provided for. And once you add a load torque, in addition to the frictional component, you need a load torque component to be provided for as well. So that's why you see a step at 3 seconds. And let us look at one more scope before I rerun this experiment to look at the result in real time. So this is the load torque versus the estimated electromagnetic torque. As you can see, the electromagnetic torque, which is in red, is a little bit higher than the load torque because it has to provide for the frictional loss as well. And that's the reason you see a little bit higher value. Okay. And you see the noise reflector on the load torque, on the estimated torque, because the current has noise in it, and we use the measured current to estimate the torque, and that's why you see a noise. But as I mentioned earlier, if you increase the switching frequency, it's not noise, it's ripple. So if you increase the switching frequency, the ripple content should be much, much lower. So let's open the speed scope again, and I'll run this experiment just once more. And you should be able to see the speed as it's being run in real time. Okay. So as I mentioned earlier, Workbench, you can do both simulation and real time and using the same model. So far, I used 2 different models for simulation and real time just to keep things simple. But in this model that you saw here, it has both induction motor model, the actual motor model itself here. As you can see, when I click on real time mode, this all gets blanked out, grayed out. That means the controller decides, it has an algorithm in the backend, which intelligently decides that this is an actual induction motor there. So it doesn't have to model the motor in the controller. But once I go to simulation mode, it will show the induction motor as well become active, and you can simulate the same model. Let me just run the simulation. And as you can see here, you get the simulation results. And after I run the simulation, I can just click on this hardware view and the simulation view and go back and forth between the simulation result and the hardware results. So as you can see here, the simulation results is supposed to look like this and the hardware result is supposed to look like this. And that matches pretty well. And if there's any mistake in the implementation, the results would not match, or the parameter estimation is wrong, the results would be completely wrong. So that helps the students kind of debug the mistakes by using the same model. And you have here the estimated torque versus the load torque. And if you look at it in simulation, it will be the same. the estimated torque versus the load torque would be exactly the same. There wouldn't be a difference because in the motor model, I just used, sorry, the motor model here, I just used a 1 by JS, an inertia element alone. I didn't have a frictional component in the simulation model, but in reality, there's going to be a friction. So in simulation, you won't see a difference between estimated torque and the actual torque, load torque, but in real time, you'll see a difference. So let's go ahead and okay, so that was the electric drive slab. And the image on the top right that you can see in the slide is basically the whole hardware setup. On the left is the induction motor, the right is the DC motor and the 3 inverter module. And all of these experiments are a similar setup. So we just swap out the induction motor for DC motor and swap out the DC motor for permanent magnet, surface permanent magnet synchronous motor, all depending on which experiment we are going to be doing. So that was the first lab that we have developed and currently available on, again, the SIAMBL website. It should be, can be acquired from here, the electric drive slab kit. And as Professor Mohan mentioned, it's a University of Minnesota startup. And Professor Mohan has no financial interest in it as yet mentioned earlier. So the second lab that we are working on, that we have developed, and we should have them available starting this summer, is the WBG-based power electronics lab. So this is again an upgrade to our previous lab, which was based on silicon devices and which was made over 15 years back. And most of the components are obsolete now, and we'll be retiring that lab once this is available, starting this summer. So this board has, again, 3 legs, 2 legs, which are GaN devices and 1 silicon device. So the students, and all of these legs can be used to do all of the experiments that I'm going to list later. So the students can do the same experiment using silicon devices as well as GaN devices. It has, similar to our electric drive lab, it has an onboard controller, which allows Workbench to directly program and control this. And previous lab, we had op-amps based circuitry to do closed loop control for the buck converter, boost converter, and buck boost converters. In this, we had a digital controller, so all the control algorithms can be implemented digitally, which allows us to expand the number of experiments that we can do using this new setup. And so on the right, we have a load right now, a rheostat load. So we are currently working on replacing the rheostat load with an active MOSFET-based load. The reason is the rheostat load would require the students to be present on campus to be able to do the experiment. It would require students to modify the load. We wanted to do the whole setup remotely so that students who don't attend in-campus classes or practice engineer who take just courses online could still do the labs. So we'll be replacing that, and that's the reason why we have delayed deploying this lab and should be available remotely starting this summer. Okay, so here's the list of experiments that we can do using these new lab kits. So we have all the experiments that we could do with the previous lab, which are the buck boost converters, and then flyback and forward converters. That was pretty much it. And so those are the options that we have. I mean, on top of that, we added multiple experiments. So we have added digital voltage mode control and digital current mode control, which again will be using Workbench to control. And then we added 3 legs so that we can do both the single phase as well as 3-phase DC to AC converter experiments as well, which are new, which wasn't there in the previous lab. And so this is the hardware, this is the PCB, the power electronics lab PCB. And we have these magnetic circuits that can be plugged into, depending on the experiment that's needed. Each of these magnetic circuits can be plugged into the spot, and that particular experiment can be carried out. And as you can see, all of these cards, except for the footbridge, has 2 connectors back and front. So depending on the direction in which you connect, whether if you connect it in the back, it connects to the GaN device. And if you flip it and connect it in the front, it will connect to the silicon device that's on board. So before I demonstrate this lab, let me just answer the couple of questions. Please keep the rheostat load as an option. So yeah, that would be an option available in addition to the active load as well. So students can, if the instructor feels they need to do it remotely, they can use the active load. But otherwise, you can just use that load if that's your preference. And from Professor NJT, do you have any specific date when the power electronic lab kits will be available? So Professor, right now we're just writing the lab manual and trying to do the active load. We should have those done by the end of this month. And after that, we need to just do a couple of tests and then send it for manufacturing. So hopefully by end of May, we should, beginning to end of May, we should have the lab kits commercially available. Okay, so let me go ahead and play the pre-recorded video for the demo for the power electronics lab. And I'll be just demoing a simple experiment, a buck converter in open loop, nothing complicated. But similar to the induction motor vector control, you can build extremely complex models using Workbench, and all of those can be extended to the power electronics lab as well. So as you can see, as I increase, you can see the ripple. So I've just set the current that you see there. I've set it to AC coupling, so you can just see the ripple component alone. And the voltage waveform that you're looking, there looks like a lot of slew there. That's because I haven't tuned the probe just yet correctly. So it should be a perfect square though. So I'll just have to tune the scopes filter so that it just looks a bit cleaner. But as you can see, as I change the duty ratio, you can see the current increase and the current reduce. So that once I go to a very high duty ratio, it triggers the trip because too much current. Again, this similar to the electric drives kit, you can't do anything wrong in this kit. If the students do anything wrong, it's completely protected. As you saw, there's a panel on the top. So if a capacitor burst or something by some short circuit or some over voltage, it would still be protecting. There would be no hazard to the students in any form. And again, if there's overcurrent, over voltage, all of it will cause a trip, which will immediately shut off. And there are multiple stages of protection. We have a hardware protection, which will hardware trigger. And then there's a software interrupt trigger as well as a software control code trigger. So there's like multiple stages. Even if one fails, other would take over and shut the experiment down. And as you can see, I can vary the load. I'm just varying the rheostat here, and you can see the current increase and the current reduce as well. So that's the DC buck converter experiment. And as I mentioned earlier, we just have one experiment for the power electronics lab. We'll be adding more and more experiments, all of those listed in the detail there. Okay, and there was no control of any form here. It was just like a slider that I changed to change the duty. But again, you can put trans function, measure the input voltage, look at the output voltage, and then do some form of control. And yeah, as you can see, this is the measured input voltage and the output voltage. So on the top, you have the input voltage, and on the bottom, you have the output voltage. So these steps that you see here, the green steps, those were when I changed the duty using the slider. Those are the steps that you saw here. And the maximum duty I went to was a little bit less than 50%. So it's like a little lower than half the voltage. So it's like 19 volts here, and you get about a little less than 9 volts here. Okay, so before I jump into the next lab, let me just answer the question from Matthews, Sherry and Matthews. The power electronic textbook has analog control procedures in it. How do you provide the background material needed for digital control? Is there a plan to change the text to digital control? So Professor Mohan and I are working on a revision to his earlier book, which is the first course on power electronics. And the publisher has accepted the book, and it should be available. They should start publishing it in summer of next year. And in that textbook, we will be adding these lab sections as well for all of the chapters. And it will have the updated control algorithms as well as the workbench-based control. And we'll be also adding simulations into the textbook, both using MATLAB Simulink as well as Workbench and for all power electronic converters that we had mentioned earlier. Okay, so let me go ahead and talk about the third lab that we are currently developing. So this is still under development stage. Since last year when we gave a brief talk about this lab, we have come pretty far. We have tested a bunch of systems and have shown proof of concept. So we are pretty confident that this lab should be implementable and available pretty soon as well. So So we right now have a power system course being taught, but there is no associated lab with it. So usually most of the schools that teach power system, they use some software to be able to do power system simulation experiments, grid simulation. So we wanted to be able to bring hardware experience to the power system lab as well, and be able to not only do it for the teaching labs, but also extend it for research lab. So one of the problems with power system implementation is there are options like using Opalati, where you can implement complex grid models and then emulate the whole grid model in real time. But the problem is Opalati, as pretty much everybody knows, is very expensive. We ourselves have one of those setups in our labs, and I think it was like $100,000 solution. And even that, we need to constantly go through certain upgrades to be able to figure in bigger systems. So what we wanted to do was certainly not create a system as powerful as Opalati, but then break it down into smaller components so that each of those individual systems can emulate one particular node of a power system, and we can add as many other nodes as possible as wanted into the system. So on the left is the system that we want to try and emulate. We have a grid connected system. Say we have a motor load that's connected to the grid, and then we have another couple of generators like PV generator, wind generator, and say we have some inverter-based relays and some battery storage. We want to be able to create a test setup where we can interconnect all of these systems and run all of these systems and see stability analysis, see what happens if a PV system or a wind system shuts down, what happens to the grid, whether it's stable. So again, all of these can be done in simulation, but as you know, simulation only takes you so far. Also, it takes a lot of time to do simulation of power system grid, and it's certainly not in real time. So it probably take a couple of hours to be able to emulate, say, 100 node grid. But as opposed to if you have these kind of setup, it does the whole thing in real time pretty much. And each of these nodes that are shown here is being emulated by a single control card. So the control card that's shown on the top here has a inverter module, a 3-phase inverter module using GAN switches. And again, similar to all our previous lab, it's very low power, low voltage. It's it's at 42 volts, and the power rating is 0.5 kilowatt. But the power can be extended as much as possible, as much as wanted, because you can just cascade these systems in parallel, basically increasing the power capability. So each card is rated for 0.5 kilowatt, but you can combine, say, 5 of these cards to make 2.5 kilowatt grid emulator. And so the grid emulator basically controls the output voltage that's being pumped out from this node. And then you can connect multiple other emulator cards to the system. So you could have one of those cards emulating a motor, and another card emulating a PV system or a wind system, another card emulating an inverter-based relay. So all of these can be interconnected together. And these can be, again, modeled using Workbench. So the motor emulator, PV emulator, all of these are modeled using Workbench. So in case tomorrow you want to change the whole equations for a PV emulator, use a finer model, you can just go to the Workbench model and change whatever parameter you want, or add whatever control model that you want, and just completely change the whole PV emulator model itself. So you're not limited to any pre-built models or systems that that we have developed. You can modify it however you see fit. Okay, so here's a list of experiments that you can do using this whole lab setup. Again, this is just at very preliminary stages. We still haven't started writing the lab manual, so we might add more and more lab experiments and expand the capability. As Simone would say, the sky is the limit and pretty much with this kind of setup, because each of these modules have about 5 cards that can be interconnected, but you can parallel them as much as you want. Like there's no limit to it. So you can parallel 50 systems, 60 systems, 100. There is absolutely no limit. And unlike other central processor-based system like DSpace, where if you put 100 nodes, you need to have a more powerful processor. And at some point, it's going to stop working or being able to solve it in real time. But that would never be the case here, because each of these nodes are being emulated by its own low-cost processor on board this card. So you can connect hundreds of these nodes, and they're just doing their own process independently, just measuring the grid voltage and measuring the current and determining what needs to be done individually. And we have one central supervisory controller which just directs what power needs to go out from each of those nodes. So that's pretty much the only control that's allowed on the supervisory. So there's not much load on that controller. So you can parallel how many hour you want. So this is a list of experiments. And before I run the hardware, let me just answer the questions from Professor Ingetti. How does one introduce/emulate line impedance in the system? So Professor, in each of these cards, we have a line inductor, which is for filter. And we switch each of these cards at about 500 kilohertz so that these line impedance can be really, really low. So after that, we can emulate. So the lower limit is, say, we use about 100 microhenries inductance, or that would be pretty high. Let's say we use about 50 microhenry, 20, 30 microhenry inductance. You can emulate any inductance above that value. You can't emulate an inductor lower than what we have in the physical hardware, but you can always emulate higher in inductance, because all you're basically doing is reducing the bandwidth of your inner current control loop. So if you reduce the rate of the inner current control loop, basically you're going to increase the slew rate, which is pretty much like emulating a higher inductance. So you can emulate any amount of higher inductance if you want. You just can't go lower than what we have put on the board. Again, we can reduce the lower limit more and more as we go to higher switching frequencies. So right now we have just done it for 500 kilohertz. Again, it can go to megahertz or higher. We just have limited at 500 kilohertz because we want to test our thermal system before we go to higher frequencies. Is there a way to introduce reactive power compensation via switched capacitors? I'm not sure. Let me think about that and get back to you. It should be possible, I would assume, because we can do reactive power as well as real power control using each of these cards. Again, using it as pure reactive power compensation, as you say, using switch capacitors, that's something that we'll have to think about, and I'll get back to you. Okay, and let me go ahead and run this demo. You have two inverters on the desk here. Again, this is a very preliminary prototype that we are trying out. So in the final version, it will be more modular, similar to our inverter and the power electronics module that we had. It will be more modular, where you can just plug and play, and more compact with not any of these wires just going here and there. This is just a test prototype. So on the left, diagram is showing you an inverter module, which is going to be emulating a grid. So all we have here is a stiff voltage that's being applied, three-phase voltage, to generate a three-phase output. And we are measuring this should be currents, my bad. But yeah, these three are currents that we are measuring. So we'll make one of the inverter run as a grid, and then the second inverter, which is on the right, which is connected. So the three-phase of the first inverter is connected to the three-phase of the second inverter, and both of us will become voltage source. You will be a short. So to avoid that, we have three inductors in between. So one of the inverters is applying a voltage, which is the first inverter, and the second inverter will be doing current control, drawing or pushing current into the grid. So let me turn this on and run this. And is the inverter on? Let's connect it to the first inverter, right? Okay. So what I'm going to do is first run the first inverter, put it in voltage control mode, and then I'll go on to the second inverter and load the emulator module there. Okay, you can go to the second one. So let me stop this. So right now the grid is generating the three-phase voltage. I'm not going to show you the measurement here because the emulator module is going to measure both that as well as its own voltage. So let me go to inverter 2, open that. Okay, so what we are doing here is we are measuring the voltage applied by the first inverter, getting the theta, and then we are measuring the current, and we are trying to inject a current 1.5 ampere with 0 in the Q axis. So what I'm basically doing is having only real power being pushed, real power being pulled into the system. So it's like a real load. I can't say it's a motor because a motor would have reactive power, or let's assume it's a PMSM motor where you wouldn't have reactive power or negligible. PMSM motor in vector control with no field weakening. So you'll only have real power being drawn from the grid, and there would be no reactive power. So that's what we are trying to emulate here. We have a real power and zero reactive power. So what it's basically trying to do is trying to draw this amount of current from the grid. So we are measuring the grid voltages, converting it to DQ transform. And then in DQ transform, we want this much amount of real current and zero reactive current. And then we figure out what voltage needs to be applied on the second inverter so that this amount of current is drawn from the first inverter. So that would effectively make the first inverter think as if it's actually connected to a PMSM motor that's drawing constant current. So let's go ahead and run this and look at the voltages in the current. All right. There we go. So let me stop this and run it again so that you can see it as it's logging in real time. Okay, so let me stop this and look over the results. So this is the applied voltage. So this is the voltage that the motor applies so that this desired current, IDIQ currents, flows into the motor. So this is the three-phase ABC voltages. You can zoom in a little bit. As I mentioned earlier, there's limited data logging capability. I will shut off a couple of more other scopes so that you get more data logging here. But this is what you get, the three-phase voltages we measure using the workbench scope. But again, I'll show you a higher bandwidth version as well in a second. So this is the three-phase voltages that are applied by the second inverter to get the desired current. So this is the current that is measured. Again, it will be a bit choppy, but I'll change the scope settings so that it becomes more finer. So this is the three-phase current, ABC current. And if you look at the IDIQ currents, again, IDIQ is DC component, so it's much more smoother and cleaner. So what we requested was 0 ampere in the reactive component and 1.5 ampere in the DQ real component. And as you can see here, you get it settles down to 1.5 ampere and the reactive component is 0. So this is basically emulating a constant current load in effect. Okay, so let me shut off a couple of scopes and let's look at the current again so that it's a bit cleaner. Okay, and this again. Okay, and let's zoom this. As you can see, the currents are now much smoother than what we saw before. So yeah, so as I mentioned before, the logging capability is limited. So the more channels that you add, the lesser the number of data that you can see more with higher resolution. So the more and more scopes that I add on in real time, the lesser and lesser the resolution is. Similar to a DSO, when you connect just one channel, you have 100 million samples per second. But when you connect two channels, it becomes 50 million samples per second per channel. So pretty much similar effect that you see here. And we are planning on adding a high-speed data logging capability here as well in the future. Yeah, so that concludes the power system lab, and there's just one other final thing that I need to mention. And before that, let me just answer Professor NJT's question about a typical distribution system has resistance, impedance transformer, and load at each node. Other nodes may have PV generation / energy storage. Not sure how one conducts such experiment with proposed power system kit. So Professor, as you can see on the right here, this slide, right bottom, the emulated grid does emulate all of those components. So in this one particular emulation model that we are currently doing, we are emulating a grid, a connected system, a grid connected motor system, and then we have a fault condition on the grid, a single phase to ground fault, and we emulate the full system, the delta to Y transformer, and then the line impedance connecting from the transformer to our motor, and then the point at which the fault happens, and then the interconnection between the fault and the motor load. So this full system we are going to be emulating using this emulator card. So when I showed you these modules here, basically saying we are emulating motor, PV, battery storage, these weren't just interconnected systems as actually shown here. Each of these have, in addition to them, emulation modules for the transformers, line impedance, and all of those that make part of the grid. So there are two applications where we are targeting this. One could be to teach a grid stability on all of those experiments. And the primary focus, though, mainly is to do microgrids, both AC and DC microgrids. So where you would typically have systems similar to this, where you have a central generator, like a DC generator, and then smaller loads, which are connected directly without most likely transformer or anything. And even if there's a transformer again, we can emulate, and we have already emulated all of those systems in the model that we developed. So yeah, it's yeah, this diagram on the left is pretty misleading. It gives the impression that we are connecting all of these systems directly to the grid, which of course won't be the case. There's going to be some kind of transformer and transmission line parameters that come into the picture as well. Okay. So yeah, that's pretty much it. And oh, sorry, there's one more question. Is the new electric drives in the new electric drive system? How would you compare processing speed to DS1104? So the DS1104 had a ST microcontroller with a 250 megahertz clock. The current platform that we use as a TI microcontroller, TI DSP, with a 150 megahertz clock. So the performance is very close. The ST microcontroller was around like 20, 30 years old microcontroller that was introduced back then. So the, oh, sorry, just the lab light went off. One second. So yeah, the TI microcontroller has more capability in that it has multiple parallel instructions that are available, which makes it way more powerful in terms of processing speed compared to what you would get with ST microcontroller that's inside a DS1104 platform. So there are certain experiments that we weren't able to do with the D space that we are able to do right now. For instance, previously we used to have an experiment of hysteresis control of the permanent magnet synchronous motor in the basic drive lab, because the advanced drive we do vector control, but in the basic drive we don't introduce that, so we do hysteretic current control. And we were never able to implement that using the DS1104 platform because we had to have a step time really small, and the processing speed wouldn't just be sufficient to implement it. But using our new platform, we are able to, and we do implement hysteretic based current control for a basic drive lab in the permanent magnet synchronous motor experiment. So the performance is, if not equal, it's if not better, it's equal to what you would get with a D-Space platform. So this is our the final controller that we have. This is for research purposes. So a lot of people who have been using the drives have asked us if they can make their own inverter, but just use the Workbench platform because it's easier to implement, and use the controller to program from the Workbench platform rather than writing code. So because all of our system are developed for teaching lab, it's 42 volts low power, and for research, it's not applicable because people want to usually do higher power. So we made this small microcontroller breakout board, which can directly connect with your with Workbench platform, and it has all the requirements to do any kind of power electronic control. So it has all the PWM channels, ADCs, and communication channels exposed, and you can connect it to any inverter hardware or any power electronic hardware that you have, and use Workbench to directly program it. And as I mentioned earlier, the platform has very similar capabilities to a D-Space platform that you get with $9,000. And right now we are manufacturing this, and the cost is somewhere between $25 to $30 per unit to acquire this particular system. So that's the final thing. And I just want to briefly mention about the fourth lab, which is in very preliminary stages. Professor Mohan had mentioned it briefly. It's the Advanced Power Electronics Lab. And there's a whole bunch of experiments that we had that we are working on developing. Hopefully, one of the students that Professor Mohan has hired for the summer will be able to do some of those lab modules. So this is the hardware. So I just want to show the capability of what we can do for power electronics using Workbench, so that we can be confident that we can use it for all the advanced electric drive lab experiments that we have promised in our ONR proposal. So this is the hardware that we used for controlling our matrix converter hardware that we made. So we have a TI DSP and Xilinx FPGA. So this is an older variant. We will be replacing it with a much newer Xilinx processor. So this whole hardware can, the DSP takes care of all of the control algorithms, and the FPGA mainly just 4-step commutation. It is only there for commutation purposes and does no control algorithm. So here's the whole hardware lab. So this is very high powered. So it's relatively high power compared to our teaching labs. So it's a 5 kilowatt matrix converter hardware and operating off of line voltages. And so this is the whole model developed using Workbench to control the particular matrix converter hardware that I showed earlier. And you can build really, really complex systems. So I'm using here direct space vector PWM modulation for a 3-level matrix converter. And within each of those modules shown here, there's a subsystem which goes much, much deeper and more complicated with significant amount of trigonometric operation. And the TI controller that we use in the code that's being generated by Workbench is extremely optimized so that it can run in real time. And this is the results that we get, the input current and the input voltages, the output current and the output voltages, phase and the line voltages. So this is one of the experiments that we will be adding into our advanced power electronics lab. And this is for research that we developed, which was a little bit high voltage and high power. And we will be scaling this down completely to, again, 42 volts so that when the students do the experiment, there is no hazard that can happen. But as I mentioned earlier, we have the breakout controller available. So if someone wants to extend all of these experiments to higher power, they are more than welcome to extend. And we will be making these high power boards available as well if somebody wants to use the high power board instead of the low power, low voltage variation. So with that, I would like to stop there. And if anybody has any other questions, I'm more than glad to answer. And thank you all. And I would like to thank ONR for funding this project, both the software development, which was the previous grant, and then all the new hardware developments as part of the ongoing grant. And that's pretty much their grant has made it all of these possible. Thank you.
Thank you, Siddharth, for excellent presentation. Very exciting. And what Professor Anjari asked, line impedances, they could be probably emulated through power electronics. So that's, a further project we can think of, some more research to do. And so it's very exciting that you can make this whole 5-node microgrid at, let's say, about $3,000. So one of the things that Dr. Chakravarti mentioned, that they have, I don't know how much money, there's a $40 million grant to San Diego, University of San Diego or San Diego State, I forget, for a campus-wide grid. Well, we can simulate that here. You say if you can go to 100 nodes, you could put them in parallel, so to speak, so you can emulate the whole thing, perhaps for what is 3,000 times, if each $3,000 unit has 5 nodes, so for 100 nodes, you multiply 3,000 by 20, so that'll be 60,000. So you could, at a very low cost, emulate the whole thing and show the control. So just an idea. We can go forward. So thank you very much. We're running behind time here, so we should move on. All right, so from here on, we have course developers talking about the courses they have developed, and we have to change the order. We have to change it because of the time conflict of some of the developers. So the very first one is Professor Chanan Singh. He is with Texas A&M, a very famous professor. He is a Regents professor at Texas A&M. And for the sake of saving time, I'll not read detailed bios of any of these developers, and they're welcome to introduce themselves and talk anything they would like to talk about. So Dan, at this point, could you please make Professor Chanan Singh a panelist so he can present his slides?
Yes, I have made him a panelist, so
yeah, sure.
You should be able to.
Mm-hmm.
So Ned, who is presenting? Me?
Yeah, we see you, but not
okay.
So how
yeah,
are you
I got today because I was needed something. That's okay.
Thank you for joining us for one thing. Yeah. I know you have some time conflict.
I think good to see you in the picture.
Yeah. Yeah, likewise.
So how can I share my screen?
You must have some share screen.
Yeah, share screen. Yes, yes, yes. Okay. All right. So I'm going to talk about some of the modules that we developed for Professor Nedmon on the reliability modeling and evaluation. You know that traditionally these days, many ISOs, they use the reliability tools for the source planning. For example, if you take the case of New York ISO, every 2 years, they do studies for the reliability need assessment for the next 10 years. And the tool that they use is the one developed by General Electric, which is called MARS, M-A-R-S, which is a multi-area reliability evaluation tool. And actually part of that was developed by us. So the purpose of these modules is to give the educational background for what is being done, what can be done, and give enough knowledge so that people can develop their own things. So having said that, now the complexity of the power grid is increasing even more. And some of the factors which are increasing to the complexity, they are like renewable energy sources, like wind generation, solar power, and they are very different than the sources we used to have, because you can have them, but if you don't have the wind or the solar power, you don't have the power. Then there are a lot of cyber physical interactions coming into the play because of some of the designs in the substations, some of the interactions at the distribution level, and so on. And demand response will be a big thing. It is mostly it's not implemented in detail as yet very widely, but it has a lot of potential. So basically, when we talk about the reliability, we are talking about uncertainty, because if we do not have any uncertainty, then there won't be any issue. So when we have increased complexity and uncertainty, the potential for the possible failures with significant impact on industrial complexes and society increases. And we have seen the evidence of that in ERCOT in Texas, and we were subject to power outages. Even in my home, we were losing power every half an hour and getting half an hour. Now, that kind of thing probably could not have been captured in the normal planning process, because this event, this weather, was completely, in my opinion, out of the envelope. So I think generally when people plan, you have to make a cost-benefit analysis between what kind of reliability you want and how much you are prepared to pay. If you are prepared to pay more, then you can plan for a lot more things. If you have to have a cost-effective balance, then some of the things have to be traded off. So with these increased uncertainties, the maintaining of the grid reliability will be an important objective. For example, our current administration, they want to go to zero carbon in the, I think, by in the next 15 years, which is a very ambitious goal, but there are a lot of issues that have to be taken care of. Now, the important thing is that in the power systems, you cannot just design, implement, and then see what happens. Because these things, when you put them in place, they are expensive. They are not easy to modify. So that's why in power systems in general, and also in the reliability, if you want to maintain the grid reliability, it's very important that we have model-based analysis, and we should be able to analyze and predict the effect of what we are going to do, whether it's in the planning or in the design, and then do all these things before the implementation. Because once you have done the implementation, it may be too late or it may be very costly to retrofit. So in these videos that we have, we are trying to focus on the quantitative reliability because the qualitative reliability doesn't make much kind of, it's not of much use, you know, that when we are trying to do the cost benefit analysis or making decisions and so on. Now, there's a substantial body of techniques which have been developed on this topic. So this is not something which is just from yesterday. So before I go further, once you have developed the quantitative measures, or when you can calculate the quantitative measures, that if once you have you can see that what the reliability would be, then how do you implement them? So you can implement them as a constraint, which is being done mostly these days. Because if you go to New York ISO, if you go to PJM, if you go to New England ISO, they have this criterion of 1 day in 10 years, which means that you will not have loss of load or loss of power supply at the bulk power system more than once in 10 years. And so that's the kind of criterion people have been using. You can also use the reliability what can be included in the cost optimization. You can put everything on the cost, and then you can optimize and say, okay, this is how much reliability I will have. This is how much cost I am prepared to put, and so on. And then you can have multi-objective optimization with reliability as one of the objectives. So we developed 5 videos for this course, which is a kind of a shortened version of the full semester course that we teach at Texas A&M. And so these, I think there are 7 modules. One of them is the introduction to quantitative reliability. What's the need for quantitative reliability? Not only in power systems, but you can do in the power electronics and so on. And then because we are dealing with the uncertainty, so therefore we need the probability theory and the stochastic processes. In this video, we basically focus on the probability theory. We did not have the space to go into time to go into the stochastic processes, but the probability theory, and a lot of things can be done with whatever the material over there is. Then those are 2 beginnings are kind of general. They are not only for power systems, but for just reliability. Then in the 3rd module, we have the introduction to power system reliability, that how we measure power system reliability, what are the indices, and so on. And then basically we have three hierarchical levels. And one is a single area where we basically try to consider the aggregate load and generation and see that whether we can meet the load. Then there's the multi-area reliability, which is the most commonly used tool, which I'm talking about the MARS by the ISOs now, where we have several areas and they are connected together by the effective lines. And then you try to see that how you can have the reliability when you can use the reserve from different areas. Then we cover the Monte Carlo simulation. Monte Carlo simulation is a very important tool because there are many analytical tools, but they are more complicated to learn and implement. But Monte Carlo is perhaps the simplest technique to learn and to implement, And it's being widely used because it can deal with not only is simple to learn and implement, but also this is very flexible. You can incorporate a lot of details into the Monte Carlo that you cannot do in the analytical methods. In analytical methods, you have to do some idealizations. And then we deal with the composite system reliability. Composite system means that it's like multi-area reliability, but the transmission lines are considered in a lot more detail. So this is what we cover in these 5 videos. But I noticed that Professor Nagmon's website also has slides only. There are 2 titles over there I saw. One was the videos and the other is the slides. And that's very nice because the slides has a more extensive material on this course under the title of slides. And to give the credit, these slides were developed partly under the support from the Department of Energy project, which was funded to PSERC, the Power System Engineering Research Consortium. So this is to be kind of acknowledged, the support of both DOE and the involvement of the PSERC. So now these slides can be used for semester-long course, and that's what we do. We use these slides and perhaps a few more in the course that I teach every year at Texas A&M. Now, there are several excellent books available on this topic. I have not prepared a list of all of them, but I just listed the latest one that was written, and that was by us, by myself, with my 2 co-authors, Dr. Jyoti Jadayan and Dr. Mitra, Jaideep Mitra. So this book is perhaps very comprehensive, and if people want to go into more detail, they can use this book in collaboration, collaboration with these slides on the slides, and that will be very extensive material. So I think that's what I have to say. So if there are any questions, I'll be happy to answer.
So Kanan, thank you very much. If any questions come up, we'll forward them to you.
Okay.
And, I don't see him right now, but so this is one of the most important topics, and these Texas outages, including your home, indicate how important this reliability is. And as we move more and more towards variable renewable energy sources, it'll become even more important. So,
yeah, I think I forgot to say, I will say that if we are going to go into that large scale renewables, then storage is going to be very important.
Yeah.
I think without storage, it's going to be very hard, very risky also to have all this large scale sources.
Yeah, without storage, we'll be freezing in the dark here, and you'll be boiling in the dark.
I know.
So, no, something I hope is very well planned and the reliability is taken into account.
Yeah,
So,
I think one thing which, of course, I may add is that some of the variability can be moderated if we have a strong transmission grid.
yeah,
Because what we found in some of our studies is that, for example, we try to see that if we connect Texas wind generation with West USA like generations, wind generation, then the effects get a lot more even because of the diversity of the resource, diversity of the wind.
sure.
So I think if we have a strong transmission system, this can reduce the need for storage. But I'm positive that without storage, it will be very difficult.
So certainly having an interconnected system has its advantages. And
There's no question. I think one of the things we had was that Texas is not really too much interconnected. But unfortunately, even our surrounding areas were having problems. So I don't know that how much the interconnection might have helped in this situation. But I think a strong interconnected system across the continent will be very useful.
all right, Sam, thank you so much. I really appreciate taking the time, not only to make these videos, and the slides will be extremely useful if somebody wants to teach a course on this topic. Also taking the time today to tell us about it in a very concise manner, what this course is all about. So
Thank you.
Yeah, thank you again. So we move on. So next speaker we have is Mr. Mani Maran Govindaraju, and we have to change the order of speakers to accommodate the speakers and their scheduling conflict. So Dan and Jairam, if you could please give Professor Mani Maran Govindarasu the panelist status so he can present his slides. So Mani Maran, just a very brief introduction. You are a well-known person in cybersecurity field, and as we are finding out that it's probably one of the most important areas there is, cybersecurity, because there are many bad actors out there. So, I know that you're an expert on that. You teach courses at Iowa State. So for the sake of time, I'll not read your bio, and the platform is yours. Thanks.
Yeah, good morning, everyone. Can you hear me?
Yep. Yeah, we can hear you.
Yeah, thank you. Thank you, Professor Mohan, for the opportunity to be associated with your program, and it has been a great experience. I've also had the opportunity to visit your utilities, many utilities in the state of Minnesota, close interaction with those real engineers in the subject of cybersecurity, starting now more than 10 years now. We have been doing R&D and also education in this area. As you know, these course modules are available as part of your program, but there are ways to enhance those courses with the various revisions and other things. I would look forward to working with you as we go forward. With that, I would like to sort of give you an overview of this course itself. As Professor Mohan mentioned, I teach a course, Cyber Physical System Security for Smart Grid at Iowa State. In fact, I teach that course this semester. It's a semester-long course with a lot more details than what I kind of have a module as part of this program. But the one I teach at Iowa State also has a lab and other things. But the course as part of the CUSP program does not have the lab yet. So, but there are ways for us to collaborate more to enhance the course that you have. I want to give you an overview about this course. As Professor Mohan mentioned, cybersecurity is a very important field, not just for the United States, but also around the world. Globally, all the nations are focusing on cybersecurity for critical infrastructure, including the power grid. There are various incidents and so on. So whatever I'm going to present today, it kind of covers slides that are part of this program. One or two slides I kind of added to sort of bring some new content to be aware this is very important. So, so the course itself has structured into 4 modules. One is, giving broad introduction to SCADA, automation, introduction to information security, those kind of concepts, so that it's broadly accessible to different audience. As you know, it is an interdisciplinary kind of course. Someone with the power engineering, they need to have some exposure to cybersecurity. That kind of thing is introduced in the module 1. Same way, somebody with a cybersecurity background, they have to be exposed to some power grid concepts, that kind of introductory information that is captured in module 1. Module 2 is about cyber risk assessment and risk mitigation. Professor Chanan Singh talked about, you can't anticipate everything, especially when it comes to cyber risk assessment. You can't model the adversary in a quantitative way. We will see briefly, it's very challenging to do risk assessment from a cyber risk perspective. There are methods and how we go about mitigating those things. Those are covered in module 2. Module 3 is about various communication protocols that are part of the grid environment. That is what being discussed. Then module 4 is the cybersecurity standards and best practices. As you see, this course is now one course which kind of covers broadly multiple aspects, both from an academic perspective, also from an industry perspective. That's why this course now, the flavor is now cybersecurity for the smart grid, bridging the theory to practice. It's not just talking about cybersecurity in abstract, but also in the context of industrial practices and standards, what is actually going on in the field. That kind of effort is made in module 4. So let me quickly run through. The smart grid in the modern perspective is not a physical system, it's a cyber physical system. You see this diagram that is from NIST. It came up almost 10 years now. You see the bulk power system, the physical system. There are a lot of communication and control that is happening in the cyber layer. There are sensors of all kinds. So the cyber layer getting enhanced more and more as part of the smart grid initiative over the years. And that means they are also susceptible to attacks. So how do we protect? How do we systematically make sure the cyber communication and control elements are protected against adversarial actions like cyber attack, malware, hacking, and other kinds of things. So we have to view this whole modern grid as a cyber physical system as opposed to just being a physical system. So as I mentioned, the attack surface is increasing because of more sensors and controllers and communication that are being added. There are multiple attack paths exist. You see on the right, the diagram, the internet is there. There are connectivity to the grid through corporate servers or market system servers and things like that. There are remote operations from the internet to even the SCADA and the grid control network. Not every utility does, but some utilities still they do remote operations. Those are all opens up attack paths for the adversary to get into the operational system or the OT system, they call it, operational technology system, or the SCADA network. So whether it's a substation, wide area communication network, control center, there are various ways in which the adversary can get into the system depending upon the environment. It's not necessarily that I mean every entry point is protected. You may have 99% protection, 1% is good enough for the adversary to hack in and create some damage to the system. So multiple attack paths exist. Static configuration, that means it's easy to infer what's going on from an adversarial perspective. There are lack of tools and metrics, systematic tools from a sort of quantification perspective, whether it is a risk or risk mitigation perspective, increasing integration of DERs, distributed energy resources, that definitely opens up opportunity for green energy and other things, but there are also more connectivity from a cyber elements that needs to be taken care, and also Internet of Things, IoT devices and services, they are being integrated for economics, flexibility, and other reasons, but they also increase the attack surface. So cyber threats to critical infrastructure, they have been there for years, and it is growing in numbers. I just included a report that was a while ago, but this still it is true. There are attacks from protocol, intrusions, malware, most common ones that have happened recent years, distributed denial of service attack, also insider threats, not just for grid, but all other critical infrastructure. These threats are very common. So we need to sort of develop R&D and also educational programs to secure these critical infrastructures. Cyber threat landscape, it's not static, it's a dynamic, it's evolving continuously. As the adversaries now becoming more and more sophisticated, they have a lot more tools and capabilities. There is a report, DOE, NERC, high impact, low frequency event. You see that likelihood versus consequence. They kind of laid out, if you see on the right top, the high consequence event, like more like nation state actors having a highly structured attack causing a damage, like a blackout. I will show some instances. Very less likely, but they could have huge consequence. But that report is a few, maybe 5-6 years old, but this less likely has become more and more common actually. The probability of nation state actors now targeting another nation's infrastructure is becoming very commonplace. So a lot of warfare nowadays happening in the cyber domain as opposed to be on the physical domain. So this map or whatever, this threat landscape, somebody probing, very common, but the consequence is very less. Then there are denial of service attacks, yeah, more common, a little more likely, but the consequence may not be that severe. Whereas you have a sophisticated, stealthy data integrity attack, poisoning attack, only very structured adversary can do it. Very less likely, but they will have huge consequence. So one can kind of have a blueprint of what the risks are and how do we go about mitigating those risks. So one has to systematically update this particular threat landscape. It's not fixed. This was drawn several years ago by those experts from DOE and NERC, but this is constantly changing. One has to sort of develop. Again, it varies organization to organization. So it's very important that we understand the threat landscape to protect the infrastructure. So this is the incident that we all know about. First, cyber physical attack on the cyber domain causing a malicious operation or attack causing physical damage on critical infrastructure. Stuxnet that happened in 2010. Uranium enrichment facility in Iran, they were targeted, that caused the centrifuge to sort of spin too fast and causing physical damage to those uranium enrichment facility. Major attack that happened, very stealthy and sophisticated, that impacted Iranian nuclear plant, but that malware, in fact, spread into the rest of the world, so many other parts of the world, uncontrollably. It's not with the intention, but it uncontrollably malware. No, it looks for devices, equipments, and Siemens platform. It just kept spreading, but there were no reported incident of any physical damage in other countries. So the thing is, it may be intended for some purpose, but it could have collateral damage or other consequences that has happened as part of malware Stuxnet that happened in 2010. The other famous one, Ukrainian attack that happened in 2015. It was a major blackout for 8 hours or so, close to 225,000 customers without power. It used IT technology being exploited that resulted in OT, operational technology, the control system in the SCADA environment. Adversary gaining access to the control center, trippings, breakers in the substation. there were about 29 to 30 substations were compromised, mostly distribution substations, some transmission substations, causing a major blackout that happened. That is definitely a wake-up call. So one nation actor causing damage in another nation actor. So I myself had association with this kind of post attack of these things, collaborating with some of those people in those countries. But this is sort of very not very sophisticated, but it could happen in other parts of the world. That's the kind of realization came in based on this kind of attacks in the NERC in the United States, North American Electric Reliability Corporation. They have developed a lot of cybersecurity standards, CIP, I will talk about later. They keep revising based on what's happening around the world so that we can understand, we can strengthen our security compliance in the United States that's going on in North America in general. So the other point of view, this slide was not there in the original thing. It's a little recent slide. We have to have a holistic approach. I was hearing to the presentation from ONR colleague that time. One has to look at not just technology, but technology, process, people, regulatory framework. They all have to come in concert to make this whole cybersecurity problem as a sort of robust solution. So one has to have deterrence. It's not a technology problem. It's a policy and government leadership, those kind of things. United Nations and other agencies may have a role to play. Attack prevention technologies, attack detection technology, anomaly attack detection technologies, mitigation, and keeping the grid resilient, attribution, forensic capabilities. All those things are important. There are a lot of research areas. Many are pursued by National Science Foundation and also DOE, Department of Energy, some by Department of Homeland Security. Those are all important. This sort of shows a lot of technologies, whether it is a machine learning or other kind of thing you can leverage to sort of build those sophisticated technologies for cybersecurity of the grid, bringing the cyber physical system flavor. Then, as I mentioned, education and workforce development courses like this, program like this, they are extremely important. I think if you're interested, this publication is there in Proceedings of the IEEE 2017. This whole concept is illustrated there. The other, in the interest of time, let me quickly go through. The other important thing is this, when we think about cybersecurity, we should not just look at its information security solution alone or infrastructure security problem. Also, it is a control system security. The SCADA, the energy management system, distribution management system, all those control system software, they have to be secure as well. So it is a sort of a union of information security, infrastructure security, and application security. That is extremely important. They all work synergistically, not simply saying, oh, your Windows operating system is secure, I don't need to worry about in my application software by GE or Siemens or any company. No, this security has to be built into Windows operating system, Cisco routers, and also into the automation software that you use from GE or other vendors. So security has to be there at all levels so that you have a defense in depth security, so that one can sort of prevent, detect, and mitigate against stealthy adversaries. So just to give a flavor, these are all part of that course. Risk assessment is very important. Ability to assess risk, as I mentioned, risk is the probability of something happening times what is the consequence. But when we say the probability of attack happening, it is originated by a threat actor. Those are adversaries of different types, and exploiting vulnerability in the cyber layer. What is the probability of joint probability of that happening? Yeah, adversary exploiting vulnerability in your infrastructure. What is that probability? If when that event happens, what would be the consequence? So traditional risk assessment assumes what is the probability of some extreme event like whatever happened in Texas and other places, and what is the probability happening, what would be the consequence. Here, what the threat is basically adversary source. What is the probability of a state actor, a hostile nation trying to target your system? It's very hard to model. There are so many things goes on. What is their intention? What resources they have? when they are going to target. So threat assessment is more of an art than a science. So that's why the risk assessment for the cyber point of view extremely challenging. Quantitative risk assessment is very, very hard. There is quite a bit of subjective element involved. So there are a lot of research that have gone on recent years, but still it is ongoing research. Some of us know we work on game theory. How do you use adversarial modeling, interaction between adversary and defender using game theory? Those kind of projects are very relevant in this context. In fact, that is supported by NSF. So this is again risk. What is the likelihood of 2 substation, 3 substation, 2 transmission line, 3 transmission line being compromised? Essentially n minus k contingency. It's not like, k being 1 or 2. K could be any number because the adversary has a control where to attack, the space and the time when to attack. And a sophisticated adversary can orchestrate both in space and time attack vector that can cause major damage in terms of blackout or a major regional blackout of those kind. It is very much possible. So quantitative risk assessment is extremely important. There are assumptions to be made. One has to make those assumptions to have those things possible. So these are all covered in that lecture, the course module. Then there are module 3 that talks about various communication protocols that are part of this infrastructure, grid infrastructure, DNP3, that is between communication control center and substation. Within the control center, IEC 61850. Then between control center, ICCP, those protocols are discussed in this thing. They have to be secure, whether through encryption, other kind encryption for sure, but also authentication and other things. Those are all described. Then it also talks about NASPnet, which is more on the synchrophaser network with the PMUs and how they are connected. What is the cybersecurity for NASPnet? That is also described in this module. I believe it's in module 3. Those discussions happened. Here, how do you secure the phaser gateway, the PDCs, the PMUs, the connectivity between the gateways through the data bus, communication infrastructure? All those things, securities are important. Then other important thing is I was very impressed with the presentation by Raju about the power electronics, those kind of laboratory that University of Minnesota has developed. That's extremely important for hands-on learning and really understanding the physical significance of this studies of various kinds. So for that, in the same context, cybersecurity for the testbed or cybersecurity testbeds are important. One way to orchestrate this kind of testbed is physical communication and information and control layer. You can sort of plug in different platforms. There are modularities and abstraction and interfaces they have to be developed. Then once you have this infrastructure in place, one can inject attacks on this communication and the cyber layer and see what consequences it can do, like risk assessment and things, studies of that kind, and also instrument various defenses and see how effective they are. One can do cyber attack defense exercise on this platform for various use case scenarios. So these test beds are very, very important for education, workforce development, and also for doing grid exercise kind of studies. So Iowa State has such a test bed for last 7-8 years, I guess. We have used quite a bit for various use cases, including vulnerability assessment. We found vulnerabilities on industry grade platform reported to ICS CERT, Department of Homeland Security, about those vulnerabilities through responsible disclosure policies, working with the vendor in this case. Then we have done a lot of risk assessment studies. We have also done various attack defense evaluation for complex scenarios on the regional grid kind of model. And of course, we have used this testbed extensively for cybersecurity education at Iowa State. And also we have used for cybersecurity training for industry professional in state of Iowa and other parts of the country. Multiple instances, these were all supported through NSF CPS grant. Thanks to NSF for the generous support to develop the testbed and also having this impact in the community, not only in the university community, also in the industrial community. So the last few slides about connecting to the industrial practice. Of course, the testbed itself provides that flavor, but from a best practices and standards perspective, NERC has a critical infrastructure protection standard that is also covered in detail as part of this course. Its objective is about physical, cyber, and operational security of the bulk power system. It has a pretty broad range of expectations from a technology perspective, from a process perspective, from a sort of training workforce perspective. A lot of things are covered, and also reporting perspective from a incident response and restoration planning. All those things are covered. Also things like sensitive information, how to protect those things, those are all covered. This is NERC version 5. It is constantly being updated. You see there a lot of things you hear, like some are technology based, personal training, who are the personnel responsible for what, training them. Those are extremely important. Workforce training point of view. There are things like you see configuration and change management, vulnerability assessment. Those are all technical. So some of the things what you see, they are technical, some are process oriented, some are related to workforce development point of view. And they have added cyber security for the supply chain, which is a very important area. Those are all added. I think this SIP 12. Those are all in place, and it is constantly being revised so that it is up to date and in tune with the evolving threats and the vulnerabilities that are being discovered. So these are described, and also there are other best practices that is happening in DHS and also NIST. Those things are also described in this module. Just to conclude, cybersecurity for smart grid has become global importance, not just in national level in the US and North America, but it's a globally important problem. Recently, there was a report that Indian grid, the grid in India was targeted by a cyber attack. It's not still clear whether it is accurate reporting or not, but these kind of things are happening broadly, not just in the United States. I mentioned about the Ukrainian attack and things like that earlier on. So we have to sort of have collaborative effort to sort of do R&D and education in this area. It is inherently interdisciplinary in nature, whether it's R&D or education, both have to be interdisciplinary. Engineers and cybersecurity professionals, they have to come together. And one has to have a sort of holistic approach, having information infrastructure and application security, defense against stealthy cyber attacks that requires cyber physical system approach as opposed to just a conventional IT security. So CPS security is very important. Testbed I talked about for various experimentation, grid exercise, other use cases like training, cybersecurity standard, industry best practices, and those are very, very important. Education, training, workforce development programs are important, such as the program at the University of Minnesota is very, very, very important and timely program. Not just power engineering, but any broader area of smart grid is very, very important. Synergistic collaboration. I think university, industry, and government, they have to work together. And of course, international collaboration in R&D and education is critical in this area. I would like to thank everyone for this opportunity to make this presentation. And also I would like to acknowledge NSF, DOE, PCERC, EPRC, and the University of Minnesota for this opportunity. I have collaborated with many people over the years. Their names are listed. I would like to acknowledge their help in my R&D and educational programs. And many graduate students whom contributed to my research program. What I presented here is not everything what we have done. Since then, I try to stick my presentation close to what is there in that course module. It has been a few years old, but I intend to revise it with Professor Mohan as we go forward. But I hope it provided some gist of combination of what is there in the module plus what is going to come. So it's an important area. I hope you find it interesting. when you sort of try to offer this course in your as part of your curriculum, I think students will enjoy, and there is a way to do it. It's not that complex. One can make it easy and accessible to a broad range of students. That's what industry expects. The students having knowledge, not just power engineering, but also broader aspect of power engineering, like communication, cybersecurity, machine learning. Those are all important areas. So these things, I think this course fits in that kind of broadening the power engineering program in the smart grid context. I hope this is valuable in that sense. Thank you. And if you have any question, I would be happy to answer.
Professor Mohan, you're muted.
Okay, so let me start again. Professor Govindaraju, thank you so much for this excellent presentation on such an important topic. And also, I'd like to thank you for your offer of continuing partnership to perhaps update these modules, because I'm sure it's a very fast changing area. So we really appreciate it. And I thank you from the bottom of my heart, and we move on from here. So thank you. And so I think I am in front of the fighting line at this stage. And so Jairam and Dan, you should give me the screen sharing capability. And I think I do have it. And so let me go here. And so we have, we are a little bit behind, actually quite a bit behind. So what I would like to do is to show you the courses and the modules I have developed, because these courses have been on CUSP for a very long time. And I think if you have visited the CUSP website, you are very familiar with that. So let me open up that website here, which is cusp.dl.un.edu here. So I'll just point to these modules that we have and leave it at that. So if you go to CUSP website, you see that we have these modules on power systems, power electronics, and electric machines and drives. So let me start with power electronics. So if I go to power electronics, this is the first course on power electronics that I'm pointing to here. And I don't know if I can write on the screen here, but this is the first course. And I think I cannot, but that's okay. I hope you can see my pointer in sort of red or pink is the power electronics first course. Then we have digital control of power electronics. This is made by Professor Nathan Veazey of Marquette University. And then we have two courses related to advanced power electronics. And one of them would be described by Professor Bill Robbins. He may wish to use my technique for the sake of time. And then there is a whole course on WG, wide bandgap devices, that is made by Professor Anant Agarwal of Ohio State University. And Captain Peterson referred to this course here. Then on power systems, we have a basic course, electric power systems. Okay, and so that was developed here at the University of Minnesota. And then you have advanced power systems courses here, modules here, I should say. There's a module on HVDC transmission system, okay? And then power system protection, that's Pratap Mysore, and he is on the agenda. He'll describe that. And then Professor Wallenberg developed this course, Power Generation, Operation, and Control. So he is also present today. He'll describe that. And electricity markets. So that's Professor Ross Baldick. He developed that course. And I also should mention that in this advanced power, in power systems 1 and 2, there's a module on power quality that Professor Surya Santoso from University of Texas developed. So he'll talk to us about that. Then when it comes to electric machines and drives, this is the basic course, electric machines and drives, that I developed. And then there's a vector control of drives that also I developed. But these two courses have been kind of merged into this course that you see in sort of orange here. So, in just in one course, perhaps you can bring in both. Okay, the basic electric drives course, and as well as the vector control course in one course. And then we have a finite element analysis course, which Professor Jonathan Bird developed from Portland State University. And he uses this NSYS Maxwell as the, I'm not sure if he uses that as JMAG, I forget, but he uses one of the finite element analysis programs to describe this machine design course. But then we have a kind of a higher level course, electric machine design, that is developed by Mr. Jim Hendershot, and he's here to describe that. And the other course we have is on renewable energy, on wind energy essentials. So that's the courses that we have. And so rather than going into the details about each module, let's just open up one of the courses here, maybe power electronics. If I click on that, hopefully this opens up. And you can see that it has, and every course is just about similar in structure. So there's a course learning objectives. If the students take this course, what would they learn? And there are course slides. So if you click on this, all these course videos. So for every lecture, there is a video that students can watch if you wish to assign that. And then, you could use the class hour to solve problems. So that's what we call the flipped classroom approach, where the transmission of information happens outside the classroom and assimilation happens within the classroom. So if you want to teach it that way, fine. If you want to teach it, just use one or two of these lecture modules, fine. I mean, it's just to facilitate teaching of these courses by instructors and for them to use as they fit. Then we, Siddharth Raju talked about this lab, and then we also have some, using PSpice and Plex. So that's what it is. But let me just show you a little more in detail. If I go to these lecture modules here, you will see this power electronics videos are here. So these are all, 16 minutes, or, some are short, some are long. So you have all these videos that are meant to be sort of preceding every lecture, so to speak. So I don't know how many are there. You can just see here. So let's say in a semester you have 33 lectures. For every lecture, there is a video here. I think the bandwidth is limited, so this video may not open up. We'll see. Yeah, I think it's slowly loading. Okay. So yeah, this is our internet connection. I'm speaking to you from home, and I don't have a landline here. I'm using Wi-Fi, so they are slow. But you can, I don't have to show it. You can see that I'm basically lecturing. So that's the mode that every other course developer has done, more or less. So let me, let me just talk to you about what is the defining characteristic of a course like this. What I would say is that, it is based on a switching power pole approach. So if you look at any converter, one leg of that converter, whether it's just a buck converter, a boost converter, or whether it's a converter for a three-phase drive, it consists of basically a pole. And if you could think of that pole, you can once analyze it and then use it repeatedly. Okay, so it's a sort of you can take it as a Captain Peterson mentioned this analogy of Legos. So you have one Lego block, and then you connect it in many different ways, and it will give you the type of converter you're looking for. So you can cover a lot of material in a single course. And so doing it this way, a building block approach, not only we save time, but it also shows the commonality of these converters. So we're not talking about as if they are different. And a lot of these courses are backed up by textbooks, and we're showing you this textbook, but by no means you need to have this textbook. So because all the material, all the videos, all the lecture slides which are taken from the figures in this textbook are here.
So it looks like Professor Mohan is having some internet troubles here. Please hold on while we try to get him reconnected. Just a couple minutes.
I guess I'm on, and so let me full screen. All right, so I'm back on, and so share screen. Okay, I'm sharing my screen here, share, and so here, what I need to do is go back to this, what I was showing, and hopefully you can see it here. So I was talking about this first course in power systems. So I think the defining characteristic of this course is that we cover by using a 3-bus case. One is a swing bus, the other one is PV bus, and the third one is PQ bus. Just using 3 buses and 3 transmission lines connected these 3 buses, we cover, all the way from generation to transmission to loads. And and we can also say that one of the lines is a DC line. So that is what this course is about. And there is an underlying textbook to this course, and that we are in the process of revising, because in this textbook we had examples and homework problems. They were based on Power Word, which is a very graphical and easy to use program, but in industry people are using PSSE. So we are trying to revise, coming up with a second edition that will have these examples of PSSE. And so any students who takes a course using this software would be very marketable, will be very useful. So that's the nature of this electric power systems course. And then we have 2 courses. One of them is on basic electric machines, which is right here. So let me click on this one here. And very similar to other courses, there's a course learning objective, and then course videos, course slides in the lab. So defining characteristic of this course is that it uses a very different approach. It's more physics-based than mathematically based. Okay, so rather than taking an induction motor drive and making the squirrel cage rotor and representing it with sort of equivalent 3-phase windings, we can leave it as squirrel cage. Okay, and then we use space vectors to describe this machine. So you can see that if you have flux density space vector that is rotating at synchronous speed in air gap. Okay, so again, using that approach, we can very easily cover induction machines, synchronous machines, PMAC machines, and so forth. And so that gives us the background. And then again, there's a textbook underlying this, electric machines and drives, that you see on the screen here. I won't click on it. Again, not necessary to get by any means. You just use the material that's uploaded. And then we have a course on vector control of these drives. Okay. Again, course learning objectives and course description. So I think electric machines and drives and vector control, these topics have become extremely important given what's going on in transportation industry, that these internal combustion engines, ICE-based vehicles are shifting to vehicles with electric drives. Okay, so then you think about all these wind turbines that we need as we go towards 100% renewable. So what in a wind turbine, what do we have? We have an electric drive, right? So these topics are becoming far more important than they used to be. Well, they're always important, but their importance is coming up even more so. And then we have this excellent lab, electric drives lab for the basic drives course as well as for advanced drives course that Siddharth Raju described. And then we have taken both of these courses and then turned into a single textbook. Well, we have turned into a course that perhaps can be taught without having to have 2 different courses. So that's, and this textbook, maybe if I can click on it, this textbook just came out, can be accessed here. Again, not necessary to get it at all. I just use the material that we already have uploaded on CUSP. And this textbook was published, well, it just has the PDF. Yeah, I hope we didn't upload the PDF of this text because this is a Wiley book. Okay, so I have to check as to what we have done. But so Jairam, are you online here?
Yeah, Professor.
So you should take a look at that.
Yeah, sure. Yeah.
We shouldn't be putting the Wiley material over here. Okay.
Yeah, Professor. Yeah.
It should be just the information about the textbook, okay? Because it's copyrighted by Wiley. So if you could disable it as soon as you can.
Yeah, sure.
Right. So that's that's the extent of these courses. And then we are developing this course, Power Electronics and Power Systems. And that's really the high power electronics course. And Siddharth mentioned that we are developing the lab for it this summer. So this course would have the material based around that lab. So I'll stop here, and Bill, I'll turn it over to you to describe it as you see fit. So are you there, Bill? So I don't see Professor Robbins, are you there?
Here, can you hear me now?
Yep.
Okay, I was muted. Dan, can you allow me to share my screen?
You should be able to. Well, Ned might have to stop sharing.
Oh, wait a minute, I see it.
Okay, all right, I have to stop sharing. Yeah, there we go. There we go.
Okay, I can go to what I'm going to share. Okay, I'm going to talk about a couple of the advanced power electronic modules and then a brief summary of the others. I'll talk mainly about what is called Advanced Power Electronics 2, and I'll be talking about the modules in power semiconductor devices, snubbers, heat sinks, and magnetics. And then at the end, I'll briefly summarize Advanced Power Electronics 1 in one slide and the course in wide band gap devices. So going to the next slide. Let's see, I guess I'll have to do it this way. Each of the modules that I'm going to be talking about have several components. One are exams and quizzes with solutions. And there's an example of a concept quiz for thyristors and GTOs. Of course, recorded lectures. And we also have the slides available that are used in the recorded lectures. And we also have homework problems or problem assignments with solutions. So that's the general context of the modules that I'm talking about. And as Ned has indicated, all of the other courses on CUSP have a similar set of contents. That is, exams and quizzes with solutions, recorded lectures, the slides, and problem assignments for the students. As far as the power semiconductor device modules, I probably ought to say a little bit about the way we constructed it. It's a semi-quantitative survey of modules intended for students that have power electronic design interest, but not power device design interest. It assumes an undergraduate course in low power semiconductor devices. For example, here at Minnesota, we have a junior level course that all electrical engineering students have to take on basic semiconductor devices, low power devices. The power device presentation is a fairly simple extension of the low power device background. It's only semi-quantitative. We don't get into a lot of quantitative detail. And seldom used devices like MCTs, BJTs, and so on are only sparingly mentioned. And detailed quantitative device discussions that are needed for power device design is not needed for circuit design and would probably be an overkill. And the general format of each of the device modules I'm talking about, we start with the device geometry, the terminal characteristics, the physical operation of the device, and then breakdown voltage considerations, on-state losses, switching times, safe operating area, and device derivatives and enhancements. For example, on the review of basic semiconductor physics. This is an undergraduate level, and this is just some of the beginning topics that are illustrated here. And we go on to derive the classical IV relationship and little discussion on the depletion layer and how that leads to breakdown. When we get into power MOSFETs, again, we talk about the basic geometries, IV characteristics, output characteristics. We get into losses. We get into switching behavior, again, mostly semi-quantitative. We talk about IGBTs in the same general way. First talking about the things that make it unique, such as the fact that you are flooding the drift region with a lot of excess carriers due to double injection, and so you are reducing the impedance in the on state by orders of magnitude in that lightly doped drift region, which is needed to support the high voltage in the off state. And we get into a little discussion about the parasitic thyristor that you have to avoid turning on, and to which modern IGBTs are pretty safe from unless you do something drastically wrong. We talked briefly about the real high power devices, SCRs and GTOs, and probably mention derivative devices that are very specialized. And we talk about the physical operation of the GTO and how it gets turned on, as well as the thyristor and how you can get gig control of the GTO if you're willing to have a high power drive circuit. We have a module on junction field effect transistors and field control thyristors, because some of the wide bandgap devices initially were based on these unipolar devices, which have no excess carriers put into them. And nowadays we have silicon carbide MOSFETs up to 12 or 1500 volts. So these devices are normally on devices, though they can be made normally off, but haven't found much commercial application yet. Then we get into a brief discussion about heat sinks and temperature control. We talk about what the need for temperature control is in a very qualitative way. We talk about the basic heat transfer mechanisms, conduction, convection, radiation. We bring up the idea of thermal resistance and thermal equivalent circuits, and finish with a discussion of heat sinks. When we talk about dissipative snubbers, we're talking about the classical snubbers, turn on, turn off, and so on. And all of the discussion on snubbers is just based on a buck converter. For simplicity, we don't want to get into more complex converters and the need for snubbers there, but just give the basic idea of what these various snubbers are and how they protect devices. Finally, our module on magnetics design. These are the topics that we cover: a review of magnetic circuits, and we consider what are the core geometries and what are the materials. Then we have to consider power dissipation on the windings, including eddy currents. And that leads us to a consideration of what are the thermal things that have to be taken into account when you're designing inductors or transformers. And that includes trying to bring in a very simple way of bringing the thermal considerations into account, where you assume that you have uniform heat transfer throughout the body of your inductor, including the winding and the core. And all of the heat then is dissipated out the surface area through convection and radiation. And so we come up with an approximate estimate of the thermal resistance of the inductor, and based on those considerations, and then you can set what your power dissipation allowable is per unit volume, and then go into a inductor design procedure and a transformer design procedure. This approach is only good probably for relatively small magnetic components, not for large ones where you need to do a detailed finite element modeling, but it does bring to the fore the point that we're trying to make, and that is you can't consider designing an inductor transformer without taking into account the thermal effects and the heat dissipation that is occurring. And we use an area product approach in order to do these types of designs. Well, that's a very brief overview of the advanced power electronics. There's a couple of other modules in there that I won't get into. One is on BJTs, and one is a very brief overview of wide bandgap materials, but the course I'm going to be talking about in a minute goes into much more depth. The Advanced Power Electronics 1 is a mostly on applications and on various topologies. And I've listed most of the modules here. Advanced Power Electronics for automobile applications, the dual active bridge, electromagnetic compatibility, applications of IGBTs, multi-level converters, power MOSFET applications, soft switching, space vector, PWM inverters, ballasts for gas discharge. And here I'm showing a few things that show the modules. This is just a screenshot of some of the modules that are available. I can't click on the arrow here and have it try to load because I'd probably get kicked off the internet because I'm at home too, like Ned was. Finally, we have the wide bandgap devices by Professor Agarwal at the Ohio State University. Here's a listing on the left of all the topics he covers. I won't try to read them all. You can see them for yourself, but I think you will agree it's fairly comprehensive. And I'm showing you here, again, a screen capture of a couple of the videos that he has made, and a couple of sample slides from his presentations here for a gallium nitride high electron mobility transistor, and another one, the basic structure of a DMOS vertical MOSFET. And so this is available on the CUSP website, along with the videos, the slides that are used in the videos. And I presume, I haven't looked to see if there's homework problems since this was put up fairly recently, but I would guess that there are probably homework problems and examples of exams and so on. Excuse me, I have a phone that keeps ringing at odd times because of calls from places I've never been and don't know anybody. So I think I will end my presentation here in the interest of time and see if there's any questions. I will unshare my screen here.
Okay, Bill. Thank you very much. Very concise. Those who wish to follow up, all the material you mentioned is on the CUSP website. So we'll move on here. Our next presenter is Mr. Jim Hendershot. So Jim, are you online? Yep, I see Jim. And well, I don't see him, but I see that Jim is online. So, Jim has designed this motor design course on a sort of a macro level without going into a finite element analysis. And only a person like Jim can develop such a course with almost 50 years of industry experience behind him. So, Jim, we really appreciate what you have done for us. And if you'll tell us what your course is all about, we'll really appreciate it. So the stage is yours. Can you share your screen with us?
Mute. Do you hear me?
Yeah, we can hear you, Jim.
Okay, now I have to share my screen, right? I click on share screen at the bottom.
Yeah.
Desktop, whiteboard, I don't know. Share. Allow Zoom to share your screen. I don't know why it doesn't do that. Am I muted? No.
No, we can hear you.
I got to figure out how to share the screen. Start video.
Yeah, we can see the video. We can see you.
Something now? Okay. You see anything now?
No. I think there may be some share screen button at in the bottom of your screen.
Yes, there is, and I've hit that.
And then there should be on the upper left-hand side, it says share screen.
Lower bottom corner, it says share.
Lower bottom, okay.
I don't understand that.
So Dan or Jim, do you have any advice?
You see the old guy there, but let me try this. I'm sorry for the confusion. I'm trying to share my screen. Everybody else did it. Why can't I? It says desktop, whiteboard, iPhone.
Yeah, if you can click on the desktop, that should be fine.
Yes, I have. And then share?
Yeah.
Yes.
Then open system preferences? No.
No, just share. Yeah.
Open system preferences. From Mohan, share is a two-click process. Why is that a two? Sorry.
But there are two steps. Mohan is right. First is you have to click somewhere share, kind of a square shows up, and then there's a button which says share. You don't see that?
Well, sure. Nope. I've got my screen up.
Okay.
And I hit share open system preferences. It says allow Zoom to share your screen. Oh, security to grant access. Oh my goodness. I don't know why that is.
So what we can do, Jim, is to let Professor Wallenberg come on, and then maybe you can look at that. Would that work?
I guess I don't know how to figure that out. I'll try.
Or you can send us the presentation and we can share it for you as well. That will
Okay, I'll do that. That I can do right now, I guess. Let's see. I don't know why I have more point. Let's see. Share. Okay, who shall I share it with? Upload.
So I'm sending you my email ID in chat.
Just upload? No.
So you can, you can send it to me in email if that works for you.
Upload failed. Okay, wait a minute. PowerPoint. Share. Send presentation. Okay. All right. What's your email?
So I have sent it to you in chat. So it's DEIVA002.
Oh boy. DEIVANAYAGAM, right?
No. So it's just the first. I have sent it to you in chat. Can you see that?
How about the email, Jana?
Yeah. So D as in dog, E as in elephant, I as in India, V as in van, A as in apple, 002 at University of at UMN. So at UMN.edu.
Your whole last name?
No.
D-E-I-V-A-N-A, I am. What else?
So it's D-E-I.
Oh, B as in boy? B as in boy? D
So
as in boy?
No.
So it's D as in doctor.
Yes.
E as in elephant.
Yes.
I as in India.
D,
V as in van.
yes.
A as in apple.
Yeah.
0.
Ditto. Okay.
2.
What was that?
2.
I didn't understand.
2.
Diamond?
Two.
Two.
Yeah. Number 2, yeah. Number 2.
Oh, 2. I'm sorry.
Yeah.
Yes.
At university U.
U of UMN.
UM. Yeah. UMN.edu.
Dot ED.
Edu.
Right. All right. Let's see if that works. It has no subjects. I'll send it anyway. Did that go? I hope. Cannot send mentally using my server. What? I don't know.
Shall we let Professor Wallenberg go? And Jim, you want to call me on my cell phone and we can figure it out?
Sure.
Okay.
All right. So Bruce, you're on. No worries, Jim. We'll catch you in a few minutes. Yeah, we'll catch you. So Bruce, Professor Wallenberg, my colleague, most of you know Professor Wallenberg, very famous professor, his book is used all over the world. And he's very kind to have made a course for us, which is on our CUSP website. And he has a lot of material on it, including simulation programs and a lot of questions and things like that. So Bruce, take it away.
Okay. I hope I don't have the same. I shouldn't. So you want me to just share my screen?
By the way, Jim, don't worry, we'll catch you if you can hear me.
Who am I supposed to call?
Dan Kelly.
Call me. Yeah. It's 859-539-4085.
Thanks, Dan.
All right. Let me start up. How's that?
Looks good.
Okay, now this is a course. I guess I've taught it about every way possible. I taught this course in classrooms, mainly starting at Rensselaer Polytechnic Institute. And the notes from that course became the textbook. And the co-author of the original textbook was the fellow who I took the course from, Al Wood, who was a engineer at General Electric at the time in Schenectady. And he and I taught the course for 5 years. So I went back and did a calculation, and we started in 1979. So I can't claim that I've been teaching it for 50 years. So Hendershot's got me by 10 years. So anyway, and I've taught it at Rensselaer, taught it at the University of Minnesota, as well as other places. Although this course was taught online to some students. So we have a complete Zoom teaching of this course back in the let's see, it was the fall of 19. So the basic building blocks of a power system are these three: generation, transmission. That's the high voltage where the stuff is way up off the ground, like these ones here. Please note the snow. This is, so I'm going to claim that this was Minnesota. That's not necessarily true. The generator is, this is a very large 2,300 megawatt coal plant outside of Minneapolis. And then distribution, those are the three. You'll notice that generation and distribution are the big, that percentage is a rough number, but they represent the economics of it, the dollars invested. And then transmission. It's kind of ironic that transmission is what you see all over the place, but you get into a city and of course there's distribution everywhere. The course is about power system operations of the generation and the high voltage transmission. We do not get into distribution. That's a whole new course. That's a whole other thing. The course is about power system operations, not the design of the course, although there are aspects that touch design, but it's not about the design of the course or measuring its reliability. It's about the operation of the power system. So here's the textbook. This is the latest copy of the textbook. Al Wood and I wrote the book originally, published in 1984 was the first copyright date, a second edition in 96, the last edition, 2014. And Gerald Shebley joined the team in the 90s to work on the third edition. Very sadly, I am the last author standing here. Alan Wood died 10 years ago. Gerald Shebley died last week of severe cancer. So we're very sad about that and wish his family well. I want to emphasize at the start that if you're going to write, I understand I'm talking to faculty members. If you want to write a book and you would like it to be a textbook in universities, at the minimum, you've got to have what I put at the bottom there, homework problems for all chapters, complete solutions manual, usually available through the publisher. Many people will not adopt a book without those. It seems to me like, well, shouldn't a faculty member going to teach the course understand everything so that they could do the homework problems themselves? But having a solutions manual is extremely useful. I can attest to that when I have used other books for new topics that I'm not quite as familiar with. But if you don't have homework problems and solutions, I have taught courses from what I would call a research book, meaning it's a book on all the latest to do with a certain topic, but it doesn't have homework problem. Well, then you have to make them up yourself. That is certainly possible if you put a lot of work into it, but it is difficult, and the adoption as a textbook will be much less. So that was just a little aside, but this is a book originally written in a class as course notes, and then we revised them over 5 years, and then we put it together and mailed it off to John Wiley and Company. Now the CUSP course has slides, both PowerPoint as well as PDF files. Now these are for every chapter. We have slides that you can use. There are videos of yours truly lecturing, and those lectures, you see my face in the corner, and you can see the slides that I talk about on the first line. But those videos have me talking, and they are on CUSP. The next is problem. There's a section on problem sessions. We did the course once where we said, okay, here's the slides, here's the videos, go look at that yourself. Then during the lecture, quote unquote, we did problems. And I recorded videos. I didn't have Zoom at that time. I was using something just different technology altogether. And so I recorded the videos myself with a camera. And then added those to the course. So there are videos and all the problem session files. Ned asked me at one point to write labs. The truth is, this is something that really helps the course, because there's a manual, there's a set of MATLAB programs that are on the CUSP website. You need MATLAB to run those. And there are MATLAB programs, exercises. I said here, data sets. That's mainly power flow data sets, which is a lot of data for sample power systems, along with one-line diagrams of the power flow networks, all the way up to, I used a lot of the IEEE standard ones. Probably it definitely goes up to the IEEE 118 bus. So there are some fairly large problems, and those are great for doing problem for the students to use. There are homework questions and solutions, not all of them. We find that if people write to me and ask for the solution manual, I send them to the publisher, and the publisher is supposed to see that, is supposed to find out by asking for a letter with letterhead paper, etc., hoping that it's not some graduate students who want to get a copy of the solution manual. I have no idea if it has happened, although I'm sorry, it has for certain questions. During the development of the book, I even had some of my own students that found some solutions online. Here's a quick, so that's something that can happen. Now all of those are available on the CUSP website. The essential material and mathematical for there's a lot of economics and optimization in the course. So the operation of the system, how the generator's transmission system, how they interact. If you have been following what happened in Texas last month, you know that there's I am just amazed at how many people have very, very diverse opinions on what happened. And don't ask me to opine on that, because I don't know a lot of the details, but I do know that the interaction of generators and transmission plays a very big part. What determines the price of electric energy? How do open markets for power operate? And how do we control, for example, system frequency on the network? But by the way, you can obtain a figure that shows the frequency excursion during the first hours of the problem in Texas. It is, I will use the word frightening. It is frightening. It's showing the frequency going down, 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 down to where they're load shedding, and then they force people offline. They do rolling blackouts in order on small segments of the power system in order to bring the frequency back up. The mathematical economic optimization essentials. We cover there's a chapter on industrial organization, the overall economics and finance of the power systems. How do you optimize within constraints? Very, very, this simple linear and dynamic programming. These are essential tools that we use. So we explain them in appendices to the chapter. How do you do Lagrange relaxation? That's a very useful method of solving problems with a lot of nonlinearities. What is the Gauss and Newton power flow methods? Maximum likelihood state estimation. If you're at all familiar with statistics, that comes familiar. And once you get into optimal power flow or the locational marginal price analysis, there's a whole group of optimization techniques that come up there. We'll go down through it. And I'm not going to try to go through all the details of these slides. So the general characteristics of power generation units, optimization within, these are topic outline. This is an outline of the topics that we cover. How do you actually dispatch or operate generators that are especially thermal units, and the various methods of doing that. Unit commitment is the program, is the methodology that determines what units are on and what are off and how to schedule them. That turns out to be a very interesting problem that people have spent many decades working on. Simple methods in the beginning. It was probably done on paper and then on computer with the same simple techniques. And then the first really good mathematical techniques used dynamic programming, then Lagrange relaxation, and now they use full integer programming using very sophisticated software. We talk about it, that in the text. Generation with limited energy supply. There's lots of generation, like gas units that have that can only draw a certain number of cubic feet of gas during a certain period. And how do you schedule it so that you don't run out of fuel and have to pay a very high price to operate the plant if you still need it online? Hydro scheduling is another topic that comes in at that point. That is a hydro scheduling should have a if you're going to really be in hydro scheduling, you need this is an introduction to that topic. That's a big topic and needs probably could have a whole book by itself. And transmission. Now that's the generation side. The transmission. We talk about how the power system operates, how the transmission of power, and that's basic power system course. We teach that basic course, or at least we did when I was at the university. I think we still do in the senior year. And what are the different the methodologies of calculations called the power flow. Power system security. How do we determine which outage of the transmission system might cause other lines to overload or voltages to go out of limit? And that is a topic that initially was all done with linearized methods, then with AC methods. Now, my students tell me they're just becoming lazy. They don't put a lot of analysis in it. Now they can buy stacks of computers that are on a board and they just run 10 or 20 computers in parallel doing all of these outages. I say that's lazy, but it's a superior method if you can do it, if you can get those computers. So they do that now. The optimal power flow has been the I would say one of the premier, that optimal power flow and state estimation has been one of the most researched applications. It was originally, the original paper that I recall was written by a man from France named Carpentier. And Carpentier's papers were you know, really unbelievably prescient, but it took the industry many, many years to come up with solutions that worked, the solutions that really worked well. But this optimal power flow gave us the locational price methodology that is used throughout the United States anyway. You need an optimal power flow to do that. State estimation, the genius behind that was Professor Fred Schweppe from MIT. And he had been using state estimation to track rockets and missiles using radar, which apparently you get lots of measurement data and not all of it is that accurate. So you need to estimate where it is and you want the most accurate estimation. And he realized that he could apply that to power flow, solved an immense problem that the power industry had been trying to solve for years, how to get an accurate power flow that reflects what's on the real system. The control of generation, how do you control the generation when the frequency is varying, and when the frequency starts to go down, what happens? How do you control that frequency? The frequency is the indicator whether or not you've got too much or not enough generation. And then we talk about the operation, the interchange, the pooling, brokers, auctions. And last of all, we have a chapter on load forecasting. Okay, power, the power generation operation control labs that we call them. So we have these are the topics that we cover. And the students are given a manual and they're given the MATLAB programs and data files that they can use, sample files. And then what I would do is I would say, okay, use the particular program and use this particular data file, and here's the assignment. And so it goes all the way up through load forecasting and so forth. So these are all MATLAB programs that the students can use, and there's a whole library of these data files that they can use to test the software. And so this allows them to do problems that are beyond the simple hand calculation problems. I will say this, they should always be capable of solving problems by hand. They can't use a computer when they're on a test, unless it's a take-home test, which may or may not be good for, but this course, they still have to do pencil and paper and an eraser tests in the final exam. But this is to allow them to do very extensive homework problems where they're solving with software that is not industrial grade. It is Bruce Wallenberg produced MATLAB software. Sometimes my graduate students, and many times my graduate students, perfected a lot of these. So here's an example unit commitment. If you look over here on the right, 168 hours is the number of hours in a week. That's the typical unit commitment. And I drew this up, and you can see that the first day, this is starting with Sunday. So Sunday, then the load on Monday and Tuesday, Wednesday, Thursday, it's not growing too much. Friday, it tends to grow larger, and then we're back to Saturday and the load is much lower again. And you have to have enough units on to supply the power and to have extra units in case one fails. That's the reserves. So they get this load profile and then they can adjust it up and down. I can tell them what the peak load is and then it'll adjust everything according to this curve over here. And here's a typical output, and you can see the hours. I only go for the first 24 here. and the load is going from 1100 up to 1400, and it goes much higher than that. What the generation is, you can see it runs the system on the first 2 units, and then it adds a 3rd unit in the 10th hour. And by the time you get to the peak load, you've got almost all the generator running in here. This is the kind of thing that you do. This is what it says, go to the, and by the way, all of my data sets are in spreadsheets. If you want to put your data on text files, then you're going to spend a lot of time trying to edit them, and it's a real pain. If you have it in a spreadsheet, you can find data, you can have it in columns, you can copy it, anything, you can scale it up and down if you need to. So all the data is in a spreadsheet, and the MATLAB programs read those files. And so this is an example of that. After each lecture, when I did it on Zoom, and I did it from home, students receive and I'm going to show you how I did notes with a document camera on my desk, and all of those notes I would pile in one place on the desk. And when I closed for the evening and turned off the computer, well, didn't turn it off, but got off of Zoom, I would take that stack and make sure it was in the right order and put it through a scanner. I have a scanner. It's a Fujitsu ScanSnap. If anybody needs the exact model, let me know, and I can probably get that model off the back of the thing. But it's extremely fast and an extremely good scanner. But there are many copiers and scanners. But that's very useful. Then I gave the notes to the students in a PDF file. Any printed notes that I used, they also, so they got this stash of materials. They got a copy of the notes, they got the printed notes, any MATLAB programs, those came down if they were not already in the labs. And then I created a video file using Zoom. Zoom has a very nice system and I don't understand it. They record one way, and then when they'll produce an MP3 file, an MP4 file for you. And that's a large file. So you're going to need to have something to pass it. And in the case of the students in Texas, I sent it to them through Dropbox. And all of that was put on the internet for the students. When I taught the course this way at the University of Minnesota, we used the Google cloud system that the university used, and that was very nice for the students. I just put it in there and then they got it. Students students really do like taking courses this way, especially graduate students. Many of them have lots of commitments. They don't have to be there when I'm online. Very rarely did I get everybody online live while I was live. They can attend anytime. They turn their homework by email and attachments, and I graded it. What I would do is print the homework off, mark it all up, and scan it. I would scan all their homework and send it back to them. Now, I confess, I had 10 students, so I was able to do this myself, but this is what I would also require of any graduate assistant as a teaching assistant. So here's the desk, and this is, if you're going to teach a course online, I recommend at a minimum, I would not recommend that you teach from a laptop using the laptop camera. That's just my opinion. You can see the little camera, and right now I'm looking at that camera. When we get back and you just see my face, that's the camera. It's a Logitech camera, and boy, once the COVID pandemic hit, everybody wanted one of these to be on Zoom, and you couldn't buy them. I'm not sure what the situation now, but there's the number up there. It's the HD 720p camera. And that just sits there on top of the display. And you can see the monitor and the keyboard and the mouse. You can also see my old calculator laying in there, which I guess once in a while I just wanted to pound out some numbers. And then over to the side, to the left of the screen, is on a stack of books to get the thing up in the air enough is the document camera. And there's the document camera, very, very useful. And there's the number of that. And that one also became extremely rare. I went on eBay this morning while I was preparing this PowerPoint to say, gee, let's see if this is available now. And it's generally available for about 70 bucks on eBay. I noticed there was one for $799 on eBay. And I thought, well, I don't know that guy will sell too many of them, but the prices during the pandemic were just going all over the place. eBay is a great indicator of whether something is rare, because once it gets to be rare, like for example, Dr. Seuss books right now, my wife was trying to buy some of them, wanted to get a few before they all cleared the market. And the prices in some places have just gone sky high. Well, these devices did, but they're coming back down. This thing is very, very nice. It has an automatic focus. You can move it around, and you'll notice that I have a pad there. And then I would write and I would talk. The students hear me and they can see what I'm writing on Zoom. It's a very, very good way to teach. And then the papers that I generated, as I said, I stacked them up and scanned them and sent them off to the students. And then I made videos. Here's a copy of the unit commitment video. And what you're seeing there is the document camera and my writing on the screen. I used a pen, not pencil. I didn't want to erase anything because the pen gives better contrast. And that video, the students got a copy of that video that they could watch on their own time. So I think the students, they enjoyed taking the course that way. This is a course that what we call labs can be done with software, so it doesn't need to have a quote unquote lab with the kind of thing that Dr. Mohan students need, where they actually are working with electronics. But so this was one of the first experiments I did where I taught using Zoom over a long distance. What I have not done is teach hundreds of students and had one or two teaching assistants assisting me, but that's okay. This was so I thank you. If there's any questions, I will. Let's see. I should be able to just stop sharing here, and I'm back online, and you can see me sitting here with a picture of the University of Minnesota football field behind me on the wall. So if there's any questions, how are they going to ask? Are they going to verbally? Are they going to do the Q&A?
Well, I don't see any questions, Bruce, but if they come in, I'll forward them to you.
Okay.
I think you're extremely clear, and you're also, I must say, very entertaining. So usually informative and entertaining.
Can I tell some jokes? No,
please, no jokes.
No jokes. My jokes are always clean, Ned. Now you know that.
I know. But thank you so much, Bruce. I mean, what you have done is just phenomenal. And you know that our website is used a lot. You know, Jairam has some numbers, but there are a lot of downloads. I bet a lot of them are going to your course. And because, you know, one of the things we have done, we should all take credit for it, is that we have put this material for people who otherwise don't have access to. like in developing countries, right?
I got a question from some guy in South Africa.
Yeah.
One time he said, I don't know what he'd been downloading it, and he didn't act fast enough. When the Texas course was over, they shut the thing down, and he was saying, please, I missed getting this last couple things. But yeah, I've been I was contacted by a student in Uganda. Uganda has a lot of hydro units, and he wanted to write a hydro scheduling program in the course, and he had the right MATLAB version, and I helped him a lot, and he was able to get it running. But Uganda, right? I mean, how many? That's so wonderful that we can, have effects all the way over down to some little school in country like that.
Carol, Bruce, somebody can pick up Professor Wallenberg's book and teach it, but it would be this another to have Professor Wallenberg teach part of your course. So, I think there's a lot of value to that, Bruce. So thank you so much.
Okay.
We move on. Have a good day. And move on to Jim Hendershot. Jim, are you on? Can you log on at this stage? You have to unmute yourself, Jim.
I guess you can hear me now, right?
Yep, we can hear you, we can see you, and we can see your screen.
Okay, I apologize for this.
No, don't worry about that.
As you can see, I'm a lot older now than I was when that picture's taken. Anyway, I'm going to...
We are all older, believe me, Jim.
I'm going to come to this slide at the end, but some years ago, Ned Mohan asked me to do a course on how, based on my experience, how to design electric machines. And I didn't really come up with a course. What I came up with was a series of lectures that would be used by people who want to design a machine. Like some professors around the world might like to use some of my lectures as supplemental material for their teaching method. I studied physics in school, and my degrees are in physics, and I didn't learn much in those courses when studying Maxwell, Ohms, and Lenz about how to practically design a machine. And I had to learn in industry, learn how to do it. So what I've done is created a bunch of lectures that are grouped up so that any person who is a student or someone who's starting a company or someone who wants to build a motor, design and build a motor that they can find out to buy, that show them how to get started. And so this is, these lectures are 36 lectures, and they're grouped into groups. And let's turn the page and let's look at the first group. Now, this series of lectures, 15 lectures, pertain to all motor types. And I concentrate on 3 popular motors, although there are many more. I don't cover the DC permanent magnet or DC shunt or DC series motors because those are quite old. They're still used, but there's not much design going on with them these days. Even power plant generators is a very famous old design. And there's not too many engineers that are working on new designs of those because they don't build that many every year. Most of the work on power plant generators has to do with repair. And I want to say something here that in passing, that with all these new alternative energy systems, I dearly love them all except one. I don't care much for solar. And the reason I don't care for solar is because there's no electric machines connected with solar. So naturally, if those get too popular, it'll hurt my field of interest or my business or whatever. I have designed hundreds of motors and built hundreds, probably thousands of prototypes of different types of motors. And that's where all this experience comes from. So I'd like to briefly go through, just outline what these lectures are that pertain to all kinds of motors. Some material on the operational theory, although I don't pretend to compete with physics-based or math-based teaching of electric machines. A little bit about the power converter and control strategies for the different machine types. Several of the motor types have the same control strategy, but the switch reluctance the switch reluctance machine has a completely different control strategy than most of the other ones. Then lecture 4 is what's the practical design process for electric machine? Where do you start? And what I base this on is how hard you're working the air gap. In the air gap, you're converting electromagnetic energy to mechanical work. And so to begin the design process, to size a motor, you have to first predict or estimate how hard you're going to work that air gap. And that's based on how it's cooled. Now, the next lecture, number 6, talks about the losses in machines. There are losses in the stator, there are losses in the iron, there's losses in the copper, there's air gap losses, there's losses in magnets, there are losses in rotor conductors. And so all these things are discussed, even some of the ones like proximity effect and skin effect, those AC losses are studied as well. And then in lecture 7, I talk about the difference between the analytical design method and the FEA design method. FEA design method has become very popular these days, but it's very difficult to design a machine from scratch from using a finite element analysis, because you really have to have a machine design first that you analyze with a finite element analysis, because classical formulas assume that the flux density is uniform in all the machine cross sections, but it is not uniform. It's a function of the length of the magnetic path. So the finite element analysis, all that does is to break up the cross section in a whole bunch of elements, millions of them if you need. And it assumes uniform cross section over each one of those little elements, and then it integrates them so you have a detailed analysis of what the flux distribution is across cross sections. And that is particularly important with the internal magnet machines that are used in vehicle traction today. Then lecture 8 concentrates on the discussion of the electric machine performance. And when I say electric machines, I mean motors and generators. Remember, every traction motor in every hybrid or electric car also acts as a generator during braking. So that has to be analyzed as well. Then lecture 9 discusses the magnetic materials, the permanent magnets, the conductors, and also the electrical steels that are used to complete the magnetic circuit. Then lecture 10 is very important. If you're going to begin to design the motor, you assume it's usually 3 phases, not always, but sometimes it's a 2-phase choice. Sometimes it's a 6-phase choice. Occasionally it's even a 9-phase choice. But how do you know how many poles and stator slots to use? And the average beginner in motor design, no matter how many lectures and problems he's solved with respect to math-based and physics-based analysis, has a clue of how many poles he should select and how many stators and slots. And we go into that in detail. Then lecture 11, okay, the stator configuration design, the end-turn links and the slot fill and things of that sort of thing. Then lecture 12 shows you how to design the lamination itself. I've seen a lot of beginning lamination designs that people will send me a DXF file and want us to have a sample made of that. And the cross-section configuration is just it's not very good. The tooth tips will typically saturate, and a permanent magnet machine will think it has big slot openings because the tooth tip saturates. So we discuss things like that. Lecture 12 covers the insulation systems based on the voltage and temperature. Lecture 14 discusses the phase circuits and the coil designs. There's many different designs of coils and how they're wound, how they're made. You can have parallel paths. You can, sometimes when you pick the number of turns, you find out that you've got a great big heavy wire gauge that you can't wind. So in that case, you can utilize parallel paths and increase the number of conductors and use a smaller wire size. And then lecture 15 is a continuation of that lecture. So please change slides. All right, the next group, lecture 16 through 22, covers induction motors. And there's two kinds of induction motors. A lot of people think they're the same, but they aren't the same. There's AC induction machines that are both fed from the grid. In the United States, it's 60 hertz, constant voltage and constant frequency. And then of course, there's the difference between those, the rotors in those machines for inverter powered machines. The first lecture is an introduction to polyphase induction machines. I do not cover single phase machines because there's not much being done in new work on single phase machines. And by the way, when we refer to a single phase motor, it's not really a single phase motor. It's powered by a single phase, but it's really a two-phase motor. Okay, so a little bit about polyphase induction motor theory on lecture 17. Lecture 18 is the design. What design strategies do I employ in beginning a induction motor design? And then lecture 19, the equivalent circuit parameters and measurements of those parameters and torque versus speed plots. Lecture 20, the rotor design itself. And this is a very important topic because there are NEMA standards and IE standards for rotor slot configurations, but not all of those slot configurations will work well with a inverter fed machine. So we go into those differences in great detail. Then finally, lecture 22 is we study the performance calculations for inverter fed induction machines, which are more important today than grid powered machines because there's not many grid powered machines designed because they've been around so long and they've already been designed. Let's move to the next slide, please, Dan. All right, this next group of lectures has to do with reluctance motors. And there's basically two types of reluctance motors. There's switch reluctance and there's synchronous reluctance. So lecture 23 talks about discusses the salient pole nature of a reluctance synchronous motor. And I've included some pictures there. The one cross section there from the Infolytica software shows what a typical reluctance synchronous motor looks like. ABB in Europe introduced a whole line of these with great fanfare and advertising. They won a Product 100 award in Europe with this. I don't know how successful it's been. I have no idea. But one of the big drawbacks with reluctance synchronous machines is the power factor is very bad because of the low ratio of the direct axis and the quadrature axis of the reluctance or inductance. I'm sorry, inductance. So ABB has put magnets in the flux barriers. Those are the clear slots with no color. Those are flux barriers, and the blue portion of that rotor cross section, those are the flux carriers. So we go into that in detail, and in lecture 24 as well, and lecture 25 on the design of the rotor itself. And then we study the performance analysis of reluctance synchronous machines as well. And you see on the right, in the lower right, you see several cross sections of different kind of reluctance synchronous machines. One of them is the web published cross section of ABB's RSM. Change slides, please. And 27 through 32 covers, shoot, I've got my title wrong, forgive me, but 27 through 32 covers the design of permanent magnet brushless and permanent magnet AC synchronous. Now, let me say that right off the bat, a PM brushless motor and a PM AC synchronous, they're the same motor. They're exactly the same. It's just that in the early days of brushless motors, they were controlled like a DC motor, where the speed was controlled by adjusting the voltage. And then the inverter geniuses from the AC induction motor world, they applied flux vector control to the PM brushless machine, and they changed the name of that motor to PM AC synchronous. And so speed is controlled by frequency when you control it as a PM AC frequency instead of by voltage, just like you would an induction machine, but there's no slip. Anyway, lecture 27 goes into great detail of what I just said. And lecture 28 discusses the fundamentals of the design theory of these kind of machines. And lecture 29, a very important lecture, permanent magnet rotor design, two types. SPM means surface permanent magnet, and IPM means internal permanent magnet. And just about every car company in the world now has played with or is producing IPM motors for traction for the electric vehicles. There are some new exceptions, but Tesla started with a 4-pole induction motor. General Motors started with a 10-pole. No, let's go back to Toyota. The Toyota Prius was an 8-pole PM motor. General Motors was a 10-pole permanent magnet synchronous motor. And more recently, BMW introduced a 12-pole permanent magnet AC synchronous motor. So there's quite a difference in the number of poles. Why does Tesla only use 4 poles? And why do the other ones do high number of poles? I'll let all of you think about the reasons for that. Lecture 30, performance calculations for these two types of IPM and SPM machines. And I'm not sure what the difference is right now between 30 and 31. I guess they're the same topic. Lecture 32 covers PM synchronous generator design principles. It's easier to design a motor than it is a generator because the open circuit voltage with a PM machine drops as a function of load. So that voltage drop times the current it draws, depending on the load, is the output power. Please change slides, please. Okay, the lectures 33 to 36 cover some other supplemental topics that have to do with heating, cooling, mechanical design, and some manufacturing issues. And I've even included some pictures from some of the slides here. Lecture 33 is a detailed discussion of the thermal design, what companies do to extract the heat created by the losses in the machine. And there's quite a difference between what's done for small machines and large machines. Large machines being power plant generators that have rotors that are 10 meters long. 80 megawatt, 120 megawatt machine is a total different world for thermal consideration versus a small servo motor or a step motor or a blower, or even a motor used for traction in a car or a locomotive. And lecture 34 covers cooling strategies. You see the right-hand picture under lecture 34 shows a photograph of the first Tesla induction motor. And that's a very clever serpentine aluminum piece they wrapped around the OD, and they blow air down the end that increases the surface area. That was a very clever method. They also developed a method of cooling the inside of the rotor on a PM induction machine. So, and we show pictures of those and discuss that. In lecture 35, we cover mechanical design issues for electric machines. And it's been said that the design issues for an electric motor or generator are 50% electromagnetic and 50% mechanical. Make an important note of that, because there's, you have to pick the bearings, you have to pick the preload, you have to pick the materials, you have to deal with putting the stator core inside of a frame. You can pilot bearing end shields onto the stack and have an open frame machine, or you can shrink a stator core inside of a frame. But a lot of surprises come to you. The magnetic properties of a stator core change if you have a big interference fit on a housing or a frame around it. So we discuss those things. And then we cover manufacturing practices of electrical machines, how you wind them and how the rotors are put together, and how the stator or the rotors in an induction machine can either be aluminum die cast, copper die cast, or hand fabricated from bars of whichever material and end rings. So I think that about covers it. So we've tried to cover all the issues with practical starting of the motor. And so I guess if you have any questions, I'll try to answer them. Thank you.
Well, thank you so much, Jim. Thank you so kindly for sharing your experience of 50 years and more. It's priceless, I would say, to archive these things. And, you know, electric machines are taught in only very few schools these days. Design, maybe the course on electric machines, I don't know how many are teaching it, but certainly design is quite rare. So this knowledge that you are sharing with the world would be extremely useful. And electric machine design is going to be very important as we go towards electric transportation and wind turbines. And I know that you don't like solar because it doesn't use any electric machines, but maybe we have to figure something out there. Maybe we need motors to keep the panels clean when they're covered with snow, right? So, windshield wipers, right. All right, Jim, thank you so much. I appreciate it.
Thank you.
Have a good day. So we move on here to the next topic, which is on power system protection and relaying by Pratap Mysore. So Pratap, are you online? Hey, Pratap. Yep, I see Pratap is here, but you have to unmute yourself, Pratap. So Pratap Mysore is another one of those gems. He comes to us from industry. So I claim that this course on protection and relaying should not be taught by any academic. Pardon me if you are an academic that I'm telling you this, unless you have a lot of industry experience, then you're an exception. Then I think you're qualified to teach. But a person like me should not even attempt to get into it. So because it's, you learn so much in industry by looking at all kinds of faults and all kinds of scenarios. So that's the experience that Pratap has, probably 30 or 40 years of experience in relaying. And he has been with the IEEE subcommittees on protection and relaying, and you name it. So Pratap, please tell us, but please keep it short. I think we are all getting tired. So, but just give us the gist of it. Your course is on our CUSP website, and people can go and learn from it. So it's all yours.
Are you seeing my screen now?
Yeah, we are.
Okay. Okay. Good afternoon, everyone. And I know that you have already heard and got a lot of information overload by this time. So I will keep it short here. We started this power system protection and relaying course, not as a course, but a series of lectures. So when I retired from Excel Energy after many, many years, So then, all the consulting companies in the region, they were looking for somebody to share their knowledge and then introduce to them about power system protection. Like Professor Anderson, he has written a great book from Iowa State. And in his introduction, he says that this is a course that should not be taught by professors because they don't have the experience. And then he says at the same time, these practicing engineers don't want to come and teach this course. So it has been a dilemma there. But it's, it was a great experience for me to share what I have done over my 40 plus years in this area. And then, started as a series of lectures, which was very well attended. Over 300 or 500 people were there when we first offered a course through University of Minnesota, a series of lectures. So after I retired, then this was offered as a course, and Professor Wallenberg and then Ned were the people who forced me to get into this and then share my things, and I'm thankful to them for providing this opportunity. So this, basically what we do here in this course is the objective of the course was to give some basic concepts on protection and also certain terms which are used only by protection engineers. So that is where we start initially. And then we introduce something like zones of protection, redundancy, local and remote backup protection. And also we have relay coordination to make sure that for a fault in one part of the system, you don't want to have the whole system coming down and isolating itself. And then second one is, I found that protection engineers also had to know about how to analyze faults and then find out what happens if there is a single line to ground fault or double line to ground or face-to-face fault, and then come up with analysis. This is especially useful when they are analyzing our system events. If something happened and then a relay was not supposed to trip, but it tripped, they were wondering why it tripped. Most of the times it comes out like that they had a wrong setting, but a lot of times it is lack of knowledge of the analysis that causes these kind of wrong settings. So that is why I introduced this symmetrical components concept, and then I take them through a simple exercise. Then later on, my focus was mostly on how to model this in a fault programs, because nobody uses hand calculations. I think that era is dead now. Now we just go back and enter all the values of the parameters in a fault program, and it cranks out the output. So that is where I focus most of it and then go through that. And later on provide references for further reading to enhance protection knowledge. This is especially very important. Once you get a basic concept, then you can build on it. That is how most of the protection engineers also learn, either through some seniors who are there through their practical experience, or reading papers or IEEE guides, which really gives you very good application pointers for them to use in different situations. And then of course, manufacturers are there. They have a lot of literature, and then their papers and also manuals. I tell them where to look for and get more knowledge on this. So now next one, we start with the 3-bus system.
Pratap, we're seeing the presenter mode. Could you switch the screen that your PowerPoint shared on?
Which one?
The display settings, perhaps.
What is happening now? I didn't understand.
We're not seeing the full slide. We're seeing the presenter view.
Oh. Okay. Let me see how to do this. That is not the one. Where is that presenter view? I've seen that. I think I'm seeing this here.
If you go ahead and put it back in that same mode that it was in with the presentation, there should be an option at the top of your screen to switch the display settings drop down, I believe. It's on the left. Go to the left.
Yeah, here?
To the right. A little bit. There you go. Display settings.
Oh, okay.
Swap presenter. view in slideshow. There you
Is
go.
this the one?
Perfect. Thank you.
Got it. Okay. Thanks. So now we have a simple system, 3-bus system. I got this idea from Professor Mohan. He had used it on all his, so we thought it would be consistent to use a 3-bus system, but to have different components that comprise an electric network. We have a generator, we have a step-up transformer, then we transmit power from generating station to the distribution load center through transmission lines. Then we have a step-down transformer, and then we have loads that supply power to individual homes and industries. And also we have other 2 equipments, reactive support equipments like shunt reactor and shunt capacitors that also I showed in this. So in this course, we go through individual equipment of all these and then present, what are the protection aspects of this. So if you look at it, we have generators, you have transformers, transmission lines, switching devices, watt support devices, and loads. But we also have these buses. Buses are essentially, these are the junctions of generators and others and transmission lines connected, and we protect them also. And we also protect the switching devices. And then the most important thing also is the input to the protective relays. We use current transformers and voltage transformers, and these are just stepping down high voltage and high currents to manageable levels of 5 amperes or 110 volts. These are fed to these intelligent devices, protective relays, which determine whether there is a fault in the system or not. That is what we use it. So I go through this, and this is where I give them an IEEE calculator, is a CT saturation calculator. You find out whether the relay CT actually saturated. If CT saturates, the current coming out of this is less than what actually it is. Then this course now have 22 modules available on this. So what I can do is here is I can go back and share. Okay, if you go to this CUSP site and click on power system protection, then you get the details. So it gives you where you can download the references here. I use a book from Alstom, Network Automation and Protection Guide. This originally started as English Electric Protective Relay book many, many years back in England. And then it became GEC measurements. Then Alstom bought it, so it became Alstom. Then now GE bought it and changed the name as a Network a Protection and Automation Guide. That is changed as Protection and Automation Application Guide. They have changed it. So they have changed they have gone from earth to ground now because they have Americanized the system. So it's a nice book. It's free. It's available. But this has been used very well over many years, and it provides very good basic concepts of protection that is used. And then course learning objectives describe role of main and backup protection, and you can go through and read these things. So essentially there are 22 modules which cover various aspects of instrument transformer selection. And first is instrument transformer selection, then all equipment protection, and setting examples also, how to set this. That's a very nice concept that is used here. So let me go back to my slides. So essentially you have videos, slides, and homework problems, and can go back and then refer to those, and then go, and then IEEE standards are also mentioned in every module, so you can go back and look at it. Yeah. So now a simple example, I have 2 more slides, that's all. I show you this. If there is a generator, and then if there is a fault in the generator, what do we want to do? We just want to isolate only the generator, not trip the whole system, right? Otherwise there will be a blackout. So if there is a fault on the generator, our intent is to open that breaker, okay? So now if this breaker doesn't operate, Or if we have a relay problem, we use 2 sets of relays that provides redundancy. Or if this breaker doesn't operate, what we do here is we go back and trip the breaker adjacent to that. That means initially we just restrict it to only faulted section. If that area has a problem, we go back and expand and then trip more breakers. So this is just an introduction, just a concept on what we have done. This is how every topic is introduced with a basic concept so that the student or one who is listening to this will get a good idea about what is done. It's conceptually, it gives them a very good background of what is done. Then you have other equipment, literature that is given. You can go back and read and then learn more about it. So essentially, you can either have a relay looking from other side. This is called the backup protection. That's all I had. And then I didn't want to take a huge amount of time and explain every aspect of what is done. You can go back to the CUSP site, look at that. There are 22 modules, and then we may upgrade a little bit, a portion of them. This was done long back for us. And that is what Ned and we had looked at it. And we can introduce something on IBRs also as a future response for IBRs that is not covered in this section. Any questions? I'll be very happy to take.
Well, if questions come up, Pratap, we will send them to you. And thank you again, sir, for sharing your knowledge with the whole world, actually, through CUSP. And, this is kind of priceless, I would say. We were just, Pratap, Mysore, and I, between us, we have a common research project, and I was looking at it from a theoretical point of view, and I was convinced that I was right. But then it turns out that in practice, that's not how it works. Okay, so I was in that sense totally wrong. So that's what practical knowledge and practical experience can give you on top of the theory. So thank you, Pratap, for taking the time to make these lectures, videos, and then taking the time today to share it with us. All right. So let's move on. And our next speaker is Professor Ross Baldick from the University of Texas. And he's going to tell us about restructured electricity markets. So lately he has always been very popular, but he has been even more popular with these Texas blackouts. So I don't know if you're a member of Power Globe, but there's constant questions and answers by Professor Baldick. And so he knows about markets. And I think, Ross, the markets have something to do with this Texas blackout. I don't know. I mean, the cause may be different. Cause may be that, certain things were not maintained, but probably markets had something to do with it as well, right? So
I think that's fair to say, Ned, although it's a longer conversation than that. And I might use not an adjective such as popular on the Power Globe, but annoying or TMI may be more appropriate. In any case, thank you for inviting me to present today. And thanks also for inviting me to put together the materials for the CUSP website. And I'll mention where these materials are at the end of this presentation. So I want to give a quick overview, matching the previous overviews of a class that I've taught at UT on locational marginal pricing that is broadly in the context of restructured electricity markets. So because I think most of the other presentations have been more on the technical aspects, I want to clearly distinguish what the focus of this class is, some challenges in the sort of audience, why I think it's important, the approach that I take, some main topics, and then some notes for teaching the class. So what's the focus of the class? The idea is to rigorously develop and understand the locational marginal pricing model that's used in so-called centralized day-ahead and real-time markets throughout the US and in a few other places. And this is predominantly aimed at graduate students, though at a pinch, I think you could teach it to advanced undergraduates. The map here shows plots of prices, not in this most recent February event, but from a bit over a year ago. What you might observe is that the prices can vary, in this example, from on the order of $1,000 or so per megawatt hour down to perhaps close to negative. So why does that happen? Why do we want that to happen? Why might we want that to happen? That's really what we're talking about in the context of a locational marginal pricing market. So LMP, this type of market is used in the eastern United States, mid-continent United States, California, Southwest Power Pool, ERCOT, and out of the US, it's used in Mexico, New Zealand, Russia, and other places have thought about it. The European Union, for example, does not have locational pricing, although it has zonal pricing. So although there are a few principles that are relevant internationally, there really is a focus on this that is to the North American context with a few other places. And indeed, in that context, I use ERCOT, the Electric Reliability Council of Texas, as Ned alluded. We had some serious supply and demand problems a couple of weeks ago. I use that as the main example of LNP markets, not just because we had a blackout 2-3 weeks ago, but I also include some features of other markets, principally as an example, capacity markets are relevant to other US markets, but not in ERCOT. But I'm definitely mention them so that the class is relevant nationally and internationally, building from my own knowledge and experience, ERCOT is used as the main example for most cases. It also covers a bunch of other key aspects of electricity markets. And I was struck in listening to Bruce's presentation that I owe a debt of gratitude to him and his book and his materials, together with several other people, because there is, without a doubt, overlap with his material, although we have a different emphasis. For example, we need to introduce power flow, economic dispatch, unit commitment, and some other things. But those three particular things definitely derive, and my own knowledge base derives fundamentally from Bruce's wonderful book. In addition to those typical power system-y things, if I can say that phrase, we also investigate pricing rules and incentives. Indeed, why you want to do it with why you might want to do something with a market rather than just command and control. And then in the context of a market, a very important aspect is hedging of price risk, both for energy and transmission. So what are the challenges in teaching such a class? Well, I think one of the most obvious challenge is that it really needs to put together and rely on fairly deep material in power systems. Again, I owe that to Bruce, but also to optimization. Some of that is also in Bruce's book, but also in microeconomics, principally microeconomics. And one really needs all three legs to understand what locational marginal pricing is about. And losing one leg, you can really not understand what's going on. And why is that a challenge? That's a challenge because a typical student, not just in my classes, but in anyone's class, if they have an engineering background, they might have an economics background, but they probably don't have a policy background. If they have an economics background, they might have some policy. They probably don't know a lot about optimization. A typical student, in other words, doesn't have everything that it takes to really understand what's going on. But in a class of this, I should say specialty, it's a specialty class, I can't expect to offer it just to engineers or just to economists or just to policy people or just to people from operations research. One really needs to provide it to a wider audience, at least for it to be a big enough class to make. So the first third to half of a semester is a pretty rapid review of a background material in these areas. And what I generally say to students is, you need to have an undergraduate background in at least 2 out of the 3 areas of power systems, optimization, and economics. If you only have 1, then you're gonna struggle. If you have 2, then you can coast on the 2 legs and work hard on the 3rd leg. So the expectation is that they're gonna need to spend some additional time out of class reviewing the other area. By the way, for a typical instructor, that's true too. right? For a typical instructor, we have specific background. You're probably going to need to learn up a little bit. Certainly I had to when I started learning this area on areas of endeavor that are outside of your own comfort zone. So maybe this course is also intended for instructors trying to learn a bit about it. Why is it important? Why would one put together such a class? Well, organized electricity markets have significant economic implications. I wrote this quite a few years ago, but the events 2 or 3 weeks ago show how significant the economic implications of reliable supply of electricity is, and you need technical understanding across several disciplines. Personnel at independent system operators, or sometimes called regional transmission organizations, and indeed market participants need to have a clue. And if you look at the training material available at most of the ISOs have some sort of training material, they'll tell you the mechanics of how to do something, but they won't necessarily give you many insights into the purpose and principles of the operation of organized markets. And for me, looking forward to times when we might imagine electricity markets with ever higher levels of renewables, it's not good enough to be turning out engineers who understand how it works today. I think they need to understand the principles so that they can intelligently participate in adapting to tomorrow. So that's why the class really emphasizes purposes and principles of the operation of organized markets. There's no counterpart of an organized market in other industries. So even economists struggle with what's going on in electricity markets. There are no textbooks that cover all of the relevant material. I mentioned that I owe a significant debt to Wood, Willenberg, and Chablis, but there are other books, Dan Kirshen and Goran Strubek's book, Stephen Stoft's book, that I also derive from. But I think, at least in my opinion, maybe the authors of those books might have a different view. I don't think any single textbook currently covers all of the relevant material. So I have synthesized material from several books. It's a 1-semester class. As I said, we spend 1/3 to 1/2 of the semester reviewing the background. So that'll be a coast for, perhaps 2 out of the 3 topics and a slog for the 3rd, because we'll move pretty fast. Then we start discussing pricing in an organized electricity market, the way the various ISOs are set up. First, in the absence of transmission constraints. And that's not because transmission constraints aren't important, but from a pedagogical perspective, I believe the way to understand this is to first understand it without transmission constraints, and then introduce transmission constraints and their implications. Along the way, we cover a number of other topics: ancillary services, unit commitment, energy and transmission price risk hedging, network models, and capacity adequacy, a topic relevant to ERCOT 3 weeks ago. So what are some of the background topics? I first start off with a history of restructuring in Texas. If you're in another region teaching this material, you might want to substitute history of your own region, but available on the website is the history of Texas. I should mention that I'm going to be adding another slide that covers the events of 2 weeks ago to this history. But more to the point, I think if you're teaching it in a different region, talk about the history of restructuring in your own region. Then we talk about power flow. It starts with a generic discussion of how to solve nonlinear simultaneous equations, and then power flow is a specific example of that. We cover optimization, and then as a specific example, economic dispatch. Then we cover economics, generally speaking, a discussion of microeconomics, and then particularizing to economic decision-making, both in the short and the long term. So this is, in brief, about 1/3 of the semester, sometimes 1/2 of the semester, depending on how much background material the kids have, the students have. Then we finally get onto the main topics, which is first, offer-based economic dispatch without transmission constraints. That starts off with microeconomics concepts such as surplus. We then bridge from a microeconomics concept such as the feasible production set to what that means in electricity. We also discuss why the specifics of electricity force the need for centralized coordination. Something that has been completely missing from some of the discussion in the Texas press about the ERCOT blackouts. We discuss optimization formulation, offers and bids, how dispatch works, how pricing works, the incentives, how it works when we have to curtail load, relevant to 2 or 3 weeks ago, and its implications for pricing, and then various generalizations. In the interest of time, I won't go through all of those, but various generalizations. Again, some of those generalizations are things that haven't yet been implemented, but are relevant going forward as we start to see even higher levels of renewables. Then we get on to, we put locational into locational into marginal pricing. To do that, we need to understand optimal power flow. Again, a significant debt to Bruce and his co-authors. We specialize to DC optimal power flow because that's relevant for day-ahead markets. Understand how offers and bids fit into that with examples. Look at properties, define some concepts that again relate to the economics, such as congestion rent, congestion cost. We highlight the particular relevance of contingency or security constraints, discuss a little bit about reactive power and losses and decomposition and linearization. We also discuss unit commitment as we start to bring in temporal issues, look at the mixed integer programming formulation that's now become standard in ISOs, understand why there are make-whole payments, connect back to Lagrangian relaxation, an old-fashioned way to do unit commitment, as Bruce mentioned, but one that helps us to understand make-whole payments in the context of duality gaps. That also brings us to understanding in more detail the role of prices and the implication for investment decisions. We connect unit commitment with transmission constraints and then discuss briefly robust unit commitment, stochastic unit commitment, and reliability unit commitment. And the last major topic is the hedging of energy and transmission price risk. We discuss the volatility of energy prices, their extreme variability, forward markets and day-ahead and in particular day-ahead markets as ways to mitigate that risk, the relationship to real-time markets, risk mitigation, risk hedging instruments, I should say, such as contracts for differences, how that connects to capital formation in the context of resource adequacy, transmission prices, risk hedging instruments for transmission prices, revenue adequacy, and hedging real-time prices. That should say hedging, not heading. So just to finish, detailed slides to teach this class, including in-class review questions and homework exercises, are available at my University of Texas website. There's a video recording of the class material that's available on the CUSP website. And taking Bruce Wallenberg's great advice to heart, not only are there homework exercises in the course material, and slides for that matter, but there are solutions to homework exercises which are available to instructors on request. So you can send an email to me about that, and I'm happy to send them to you. Generally, I'll check in to make sure that you're not a graduate student or a